Now let me introduce you to Mr. Jayant Kulkarni, founder member and managing director at Epicon since 1985. He graduated from VGTI in 1976 and further pursued his master's in structures in the same college. He has he has specific interest in various fields of engineering like codal provisions, seismic retrofitting, tall buildings, concrete mix design, advanced NDT and evaluation, conservation of heritage structure, and Indian aesthetics. Epicons, under his technical and administrative leadership, has successfully completed more than 8,500 projects in various avenues of civil engineering like structural design, project management consultancy, architecture and detailed engineering, assessment testing and infra. The company has received many awards, the most important one being the Industry Excellence Award by the Institute of Engineering. Now I would request Jayant sir to please introduce EFC.
Good afternoon, everyone. I welcome you all on behalf of Epicon Friends of Concrete. It's a knowledge sharing platform since 1999. We are ISO 9001 2015 certified company, and one of our defined objectives is imparting technical knowledge to society and interested parties. Even though we got ISO certified in 2005, we have started this long back in 1999 under our inspiration is great engineer A.P. Remedios. In fact, it was the first workshop or training which I had undergone with him, which inspired me that such facility should be made available for all the engineer or engineering fraternity. Next. EFC has conducted 81 workshops in last 22 years and 36 webinars in last 3 years. We started webinar series since lockdown through our unit EFC dedicated to training. The 2 photographs are previous workshop when we used to conduct physical workshop. EFC is an humble effort to create knowledge sharing platform and develop a facility for continued education for practicing structural engineers, corporate consultant, government, semi-government authorities, architects, builders, and of course, faculties and students of engineering college. Next. Our thought leader. It goes back to my teachers, Dr. V.N. Gupchup, Professor Sundaram, and now Professor Gargi, who created or generated interest in me about this subject. But the person outside my college, the first was Dr. P.C. Basu, and then subsequently Dr. Sudhir Jain and Dr. Murthy were the person who had created interest in this specific topic. Next. And of course, now our greatest thought leader is Professor Dr. Yogendra Singh. I happened to attend one program conducted by him in 2015 on 27 to 29 May at Delhi. And after that, we got introduced to each other. And subsequently, he has delivered online lectures in 9 webinars, and he has physically addressed 5 workshops in Mumbai. Next. Today, we are at webinar 137, Seismic Analysis of Tall Building using response spectrum and time history method. Our next 2 topics lined up are sustainability in May and modern trends in engineering will be in July 2023. Next. Our team, apart from myself, includes Anand Kulkarni, Ravindra Deshpande, Arvind Parolekar, Parashar Mugi, and Pandey. All of them contribute right from conceptualization to detailing of the workshops. Next. With this, I thank you all for joining in such a large number. And I welcome Satish Tapelia sir and request him to inaugurate the webinar. In fact, there is no need to introduce Satish Tapelia sir, whosoever is practicing in Mumbai, but and there can be a possibility of new generation young engineers may not be knowing him. He's a renowned consultant and civil engineer for past 45 years. That is what record says, but if I remember right, it is more than 50 years. He has adopted both conventional and modern technologies for construction in its project spanning large housing and commercial complexes, industrial project, high-rise building, sewerage and water treatment plant for private and public bodies, and also for the World Bank Credit project. Through special appointed by government authorities, Mr. Dupilia has also served as a chairman and member of many committees for collapse investigation of structures within Greater Mumbai. I was lucky enough to be part of his team when there was a collapse of Poonam Chambers, and we had carried out testing and investigation, and we could see his mastery over the subject. Mr. Satish Dupilia has been awarded the prestigious Indian Construction Industry Navaratna Award 2017. It was by Builders Association of India. With this brief introduction, can I request Dupilia sir to please inaugurate the webinar?
Thank you, dear friend Jan. I know you, as I mentioned. I was knowing you only before the Poonam Chamber and Fuji College happened, when we came real near to each other. But I've been knowing about you since many, many years before that. And I'm happy that you've been continuing your crusade for spreading the knowledge and expertise in structure and construction engineering, including coordination, quality control, etc. And nice to have you have been stomping in the various authorities for all over India, where they are known for their own expertise which they have, including government, departmental, BIS, and other areas also. And nice to have Dr. Yogesh also coming together here today to make his presentation and views on tall building analysis by time history matter and response factor matter. And sure, you'll be able to throw much more light on these various two aspects of designing. Only thing, time history method, though it can make the structure more specifically economical. The point is you must be having sufficient data available on the local area where you are planning the structure. Anyway, with those limitations, the response factor better also is quite fine. But if you want to go in very critical thing, you may go in for time history method. And surely, Dr. Yogesh will be able to throw more light on these various aspects of two method analysis. And we all look forward to his presentation and his own highly technical views on this particular subject matter. My great pleasure to showing this webinar is open. Thank you all. Thank you.
Thank you, sir. Now I request to take this issue further and start with other introduction.
Thank you, sir. Now I would like to introduce you to the director of Epicons, Anand Kulkarni. He graduated in 1987 with specialization in structures, studied for post-graduation with a specialization in structure at SPCE. He has a 34 years of vast experience in field of structural designs of various types of structures, residential, commercial, industrial, malls, multiplexes, etc. His expertise includes designing of tall buildings. He's involved in designing of more than 110 tall structures ranging from 100 meters to 250 meters in height for leading developers. He's also a member of American Concrete Institute. Some of the projects that he has worked on are Runwal Pinnacle Mumbai, Mahindra Roots Mumbai, and Raymond Towers Thane. Now I would like to introduce you to A.S. Parulekar, sir. He graduated from SPCE Mumbai in 1987 with first class honors and completed his master's in Vadodara in 1990 with first class distinction. He's working with Epicons since 1989 and has been the director at Epicons handling the NDT and Structural Assessment Department for the past 21 years. He's conducted training programs on NDT for PWD Meta Nasik, ISSC Mumbai, PWD Mumbai and Thane, Sidco Navi Mumbai, and of course, webinars of EFC. He was the appointed auditor by RMC MA for RMC plans 2012 to 12. He has worked on more than 2,500 projects, including structural assessment projects, large volume NDT projects, complex challenging structural design projects, and infra projects. He is currently handling the large industrial complex assessment at Philippines. He has an in-house well-equipped NABL accredited lab with a team of 35 engineers and technicians, and the following pictures show the in-house available equipments. Now I would like to introduce you to Ravindra Deshpande, sir. He graduated from VGTI Mumbai in 1976 with first class honors and then completed his master's in the same college in 1982. He's working with Epicon since 1985 and has been the director at Epicons Consultants Private Limited for the past 28 years. He's acted as an external examiner for PG students of Mumbai University. He has attended a training program on seismic designs of RCC structures conducted by IIT Kanpur in 2001. He's handled many industrial, commercial, residential, and institutional projects. Now I request Deshpande sir to continue with the preamble.
Good afternoon and welcome to the webinar number 137, which is on seismic analysis of tall buildings using response spectrum and time history methods. As we all know, IS 1893 has prescribed two methods for accounting the effects of design earthquake forces on the structure, namely equivalent static method and dynamic analysis method. And again, for dynamic analysis, two methods can be considered, namely response spectrum method and time history method. Code further says that response spectrum method may be performed using either design acceleration spectrum, which is provided in the code, or by using site-specific design acceleration spectrum, but with the condition that the effects of site-specific spectrum should not be less than those arising out of the code spectrum. Now, in today's webinar, Dr. Yogendra Singh will provide a comprehensive overview of the application of both these methods, especially the criteria for selection of the time history and the related issues. He will also discuss the advantages and limitations of each method and also provide practical examples of their use. If time permits, he may discuss few other topics which are related to the seismic analysis of tall buildings. In the context of the recent earthquakes in Sudan and Turkey and the huge loss of life and property, there is no need to emphasize the importance of designing buildings fulfilling codal requirements and imparting safety and structural integrity to these structures against the design earthquake forces. It becomes far more challenging when we are dealing with the real world problems. That is where the elaborations by experts like Dr. Yogendra Singh come into play, and which are of great help to all of us. After his presentation, he will also answer the questions you may have during the question and answer session at the end of the webinar. We hope that by the end of this webinar, you will have a better understanding of the application of time history and response spectrum methods, which will be of great help in solving the real life problems. I thank you all for joining in such a large number for today's workshop. And I now request Shravani to give the introduction of Dr. Yogendra Singh. Thank you once again.
Thank you. I would now like to introduce you to Professor Dr. Yogendra Singh. Dr. Yogendra Singh is currently the Railway Bridge Chair Professor of Earthquake Engineering at IIT Roorkee. He completed his graduation from IIT Roorkee in 1989 and his MTech and PhD in Structural Engineering from IIT Delhi. His research interests include performance-based design of buildings and bridges, seismic vulnerability and risk evaluation, non-linear modeling and analysis, and seismic evaluation and retrofitting of structures. He has about 30 years of experience in teaching and research and has guided 17 PhDs. He has published 85 research articles in various journals and presented more than 100 papers in national as well as international conferences. He's a member of several expert teams for post-earthquake damage surveys. He's the convener of BIS expert group on performance-based seismic design of structures. He has collaborated with NORSAR Norway, NGI Norway, NTU Singapore, Stanford University USA, University of Edinburgh UK, University of Windsor Canada, University of California US, and the University of Portugal. Now I request Dr. Yogendra sir to please start with the lecture.
Thank you very much for the introduction. Thank you, Epicons, for arranging this workshop. And I thank all of you for joining this. So I will share my screen now. And I hope you can see my screen.
Yes, sir.
And I'm also audible. I don't know how can I remove this, or it will go away after some time automatically. Okay. So I hope this bar at the top will not interfere with our presentation. So today we will discuss about analysis of tall buildings using response spectrum and time history analysis. So I will talk about ground motion recording, what we call time histories of earthquakes, and their relationship with response spectrum. And recently, our court has released a wide circulation draft. IS 1893 wide circulation draft has been released just 2 days back, and some of you might have seen that. So there are some changes in the design response spectrum. I want to give some glimpses of that also. And there are some modeling issues. I was going through the question answer column here, and some of you have already written some of the issues which you are facing in modeling. So some of the common modeling issues which I have got response about, I will talk about those also. So we will talk about earthquake, and we have discussed this earlier also, and all of you are familiar now that earthquake is just sudden shaking of the ground. And the earthquake ground shaking has some specific peculiar properties. And one peculiar property is that it is changing its direction very quickly. Within a fraction of a second, the acceleration due to earthquake shaking is changing its direction. And we take advantage of this change in the direction in our earthquake resistant design. And as a result of it, we are never designing for the full earthquake force, which will be occurring on an elastic structure. But we will design our structure for much reduced force than which will actually be applied on the structure. And as a result, our structure is going to damage during earthquake, but we intend to design our structure in such a way that it should not collapse. So in most of the structures, this is our intention to design our structures. But some of the important structures like hospitals and those structures which have hazardous consequences due to failure during earthquake, we design those for better performance, and that we ensure through an importance factor of 1 to 1.5. So, but we do not ensure, we do not have a framework in which we can ensure that whatever we are intending, we are really achieving. And that's why we talk about performance-based design. Today, we will not talk about performance-based design. We will limit our discussion to code-based design, which is basically force-based design. And it is based on linear elastic analysis of the structure, and advantage of this reversible nature of the earthquake we take into consideration through the response reduction factor R. So this response reduction factor R is of great help to us. Using this, we can avoid nonlinear analysis of the structure. Without doing nonlinear analysis of the structure, we are designing our structure taking advantage of this reversible nature of earthquake. Now, when we look at the past records of earthquakes, now we have several thousands of records from past earthquakes, and all those records are unique. Every earthquake at different sites. So if I record the same earthquake at different sites, then also the records are different. So every earthquake has its distinct signatures at different sites. And that creates a problem to us, that which earthquake we should design for, because the earthquake which will be recorded in future at the site where I'm going to design my structure, that earthquake will have its unique signature, which will be different from all the earthquake signatures which we have recorded in the past. So this creates a problem to us, and that problem we handle through identifying the major characteristics of earthquake ground motions. And those characteristics are, there are basically 3 characteristics which we can use to classify and characterize earthquake ground motions. One is the amplitude of the shaking. So amplitude of the shaking we represent in terms of the peak ground acceleration or peak ground velocity or peak ground displacement. As the term itself suggests, it is just the peak record. So when we are recording acceleration at the ground surface, whatever is the peak acceleration record, that we call PGA. And this is the most important parameter in our design. This is represented by the zone factor in our code. So we will talk about this later in more detail. Then other important parameters are frequency content. So if the structure has a period which is within the predominant frequency range of the ground motion, then there will be a quasi-resonance like phenomena, and as a result the structure will be subjected to higher response and it will be subjected to higher damage. On the other hand, if my structure is having its period far away from the predominant frequency range of earthquake ground motion, then the response will be reduced. And we take advantage of this phenomena in base isolation, because in base isolation what we do is that we make our structure quite flexible. We elongate its period to such an extent that this is outside the predominant frequency range of the earthquake, and as a result much less energy is imparted to the structure. Then the third parameter which is of interest is duration of the earthquake, because earthquake during its whole duration is causing different pulses of acceleration, and under those pulses of acceleration it is imparting some damage to the structure, and this damage is cumulated. It gets accumulated along the duration of the earthquake, and hence the total damage which will be imparted to the structure depends on the duration of the earthquake. And now people are talking about even aftershocks. So the damage which is caused due to main shock gets accumulated with the damage which can be caused by the aftershocks. So it may happen that the structure which we have designed is safe for the main shock, but it may collapse under the aftershocks. So research is going on now how to take into account the cumulative effect of the main shock aftershock series. So after a main shock, as we have seen in the past earthquakes also everywhere, in case of Turkey earthquake, that was specifically very much significant, that after the main shock, several earthquakes, and some of those were almost of the same intensity as the main shock, those are happening. So if the structure has been already damaged by the main shock, it does not have the capacity to resist the aftershocks, and as a result several structures collapsed during the aftershock. Those survived the main shock, but those collapsed during aftershocks. So this duration of the shaking which our structure will be subjected to, this is also important. However, our current methods which we are going to discuss today also, those do not take into account the effect of the duration. The effect of the duration can be taken into account only when we are performing a nonlinear time history analysis, taking into account degradation of strength and stiffness with the number of cycles to which the structure is subjected to. So that part will not be reflected in our today's discussion, but this is also one of the important characteristics of an earthquake. So the first two characteristics of ground motions, the amplitude of shaking and the frequency content together can be represented in terms of response spectrum. And most of the times we deal with, as designers, we deal with response spectrum. Rather than ground motions, we are dealing with the response spectrum. Code also provides design response spectrum. Code does not provide any ground motion for which we have to design, but it provides response spectrum. So a little bit about the theory behind this response spectrum. So response spectrum is nothing but a plot of response of single degree freedom systems, a series of single degree freedom systems. So what are these single degree freedom systems? These are the simplest structures. We can think like single story buildings, which can be represented by one mass lumped at one point. So this is having single mass and a single stiffness. So these single degree freedom systems of different periods. So here these are shown by different heights. So as the height of the single degree freedom system is going to increase, the period is also becoming longer and longer. So a taller building, a taller structure, even if it is single story, its period will be longer. A shorter structure will vibrate at higher frequency or with short period. So when all these single degree freedom systems which have different period are subjected to same ground motion, their response is very different, because the response depends on the tuning of the period of the single degree freedom system with the frequency content of the earthquake. And as a result, we get a variation of response. And if we plot that variation of the response with period, we get a curve, and that curve we call response spectrum. And here when we say response, response can be anything. It can be acceleration, it can be velocity, it can be displacement, it can be even force, it can be even stress, strain, any response we can plot. So response spectrum can be plotted in terms of any of these response quantities which I have said just now. But the most common is what we call spectral acceleration, or the pseudo acceleration of this single degree freedom system. The pseudo acceleration is nothing but omega square times the displacement. So we call it acceleration spectrum, but actually it is depending on the displacement of the single degree freedom system. And we understand that the forces in the single degree freedom system or any simple structure will depend on the displacement to which this structure is subjected, not on the inertia force. Inertia force indirectly, in turn, governs those forces, but the forces can be obtained directly from the displacement. So this pseudo acceleration or spectral acceleration is such a quantity that if we multiply it by the mass of the single degree freedom system, we get force in that single degree freedom system. That's why this is very useful to us. We don't need any dynamic analysis. We can read the response of the single degree freedom system just directly using this response spectrum if it is available to us. And the codes provide us the design response spectrum. That makes our life very simple. We just use the response spectrum given in the code and read that response spectrum corresponding to the period of our single degree freedom system. How we utilize it for analysis of multi-degree freedom systems, I will talk slightly later. But response spectrum in itself is giving us the response of single degree freedom system, which is something analogous to a single story building. So if we look at the response spectrum, let us say displacement response spectrum for a single earthquake, here this plot I have taken from A.K. Chopra's book. It is for El Centro earthquake. So the displacement, we can see that with period, the displacement of the single degree freedom systems goes on increasing. As we have seen that as the period increases, our single degree freedom system is becoming taller, it is becoming more flexible, and its displacement goes on increasing. But same is not true for the velocity and acceleration. So here we can see velocity, but it will be more informative if we look at the acceleration. So acceleration, if we see initially with period, the acceleration increases and then it decreases with the period. So this is of great help to us. This phenomena provided by the nature helps us in designing tall buildings, because if this was not decreasing with period, and we will see later, it is proportional to 1 upon t or 1 upon t square. That means this is reducing drastically with period. So if this phenomena was not happening in nature, then it would have been very difficult to design tall buildings. Let us say a 60-story or a 100-story building. The design base here has been so large that it would have been impossible to design those. By virtue of this phenomena, and this is happening because the period or the predominant frequency of earthquake, fortunately, is away from the frequency of vibration of our tall buildings. It is more in the range of frequency of vibration of low-rise buildings. So generally our buildings 1 to 10 or 15 story are in this range, in which mostly the earthquake will have the predominant frequency. So those 10, 12 story buildings are subjected to very high earthquake forces, much higher base shear as a fraction of its weight. But when we talk about tall buildings, the spectral acceleration here reduces significantly, and as a result, we get much less base shear despite much higher force, much higher weight of the building, which is nothing but a force due to gravity. And this reduction in spectral acceleration with period, actually this makes feasible design earthquake resistant tall buildings. And here this value, the response spectrum is having corresponding to zero period. So zero period is representing a very rigid structure. So a very rigid structure only will have a very high frequency or period which is tending to zero. So those structures which are very rigid, those will have almost same acceleration as that of the ground. That's why this value here, although it is difficult to obtain numerically, but this value which we estimate with single degree freedom systems having periods very small. At zero period, it is not possible to solve it, but at periods much smaller or close to zero, we can do that. And these periods we consider, you can see that there is a small flat portion shown here in this response spectrum plot. So this is representing a range which is up to 1/33 seconds. So those structures which are having frequencies more than 33 hertz, we can treat them as rigid or having zero period. And those structures will have acceleration same as the ground acceleration. And that's why this value we call effective peak ground acceleration, EPGA. And this is also called zero period acceleration, ZPA. So this zero period acceleration, which corresponds to a rigid structure, this is given in the codes, in our code, as zone factor, ZPA, a zone factor or Z, and that is also EPGA, effective peak ground acceleration. This effective peak ground acceleration depends on PGA, the peak ground acceleration which we discussed, which is obtained from the peak of the ground motion record. But it is not equal to PGA. It has a relationship, but it is not equal to PGA. So code, when it is defining different zones, it is not defining PGA, it is defining EPGA or ZPA. We have to keep this in mind. Now, other than the source, which is causing ground motion, which is the origin of the ground motion which we are experiencing at our site, the site also has a lot of influence, especially on frequency content, but not limited to frequency content. The amplitude also changes. So both amplitude and frequency content changes. And here is a problem that which we have to understand with respect to our tall buildings. So this issue was highlighted in 1985 during Mexico earthquake. So Mexico earthquake occurred something like 350 kilometers away from Mexico City. And at 350 kilometers, its intensity should have been very, very low. But what was observed that a particular height of buildings, 5-story to 20-story buildings in Mexico City, suffered very severe damage, which was not expected at a distance of 350 kilometers from the epicenter, which is far away from the epicenter. And then this phenomena was highlighted. And when they studied, there were two stations, recordings were taken at these two stations, one at this University of Mexico, UNEM, and another station was at the SCT. And Mexico City is located on bed of a dry lake. And due to that lake bed, there is deep deposit of soil. So the depth of the soil is shown by these contours. So as we see here, this is the foothill. So on one side of the city, there are hills. And as we move away from the hills, the depth of the soil goes on increasing. So 20 meter, 30 meter, 40 meter, 50 meter, so on. So depth of the soil goes on. And where this recording at SCT was made, this is having a depth of roughly 30 meters. And what we see here, this is the record at UNEM, University recording station. And this is the record made at SCT. And we can see these are plotted on the same scale. So we can see here, there is a lot of amplification. The amplitude, the PGA itself has increased drastically. It is a much larger increase in the PGA. That is one issue. And when we compare the response spectra of these two ground motions, this is the response spectrum of UNEM motion, and this is the response spectrum of SCT. And what we see here, we get a peak at 2 seconds. So normally, even what is given in our code, we are expecting the peak to occur at period less than 0.8 second. Even for our site class 3, we are expecting the peak of the response spectrum to occur up to 0.8 second. And beyond 0.8 second, our response spectrum is decreasing significantly. But here we are getting peak at 2 seconds. And this is because of the site period. So if we calculate the site period at this point, considering 30-meter depth of the soil, we get this period also roughly 2 seconds. So the site period becomes very important. And this is specifically important in case of tall buildings, because tall buildings are going to have period in this range. The low-rise buildings which are having period up to, let us say, 1 second or 1.5 seconds, those will skip this peak. Whereas in our conventional design, based on the code-based response spectrum, we are subjecting those buildings to a higher force, and the buildings having period corresponding to 2 seconds, those will be subjected to much lower earthquake force. But the site period can change this scenario drastically. And it will be at least interesting to know to you that during Nepal earthquake in Kathmandu, this peak was observed corresponding to 5 seconds. And roughly, this 5-second peak corresponds to a 50-story building. So the 50-story building will be subjected to the peak earthquake forces. And we can understand if such a peak is occurring at 5 seconds, then our tall buildings will be subjected to much larger earthquake force than what we are expecting in the design. So when we are designing a tall building, we have to keep in mind this aspect also, that what type of site period we are expecting there. This information is still not included, or any guideline regarding this is still not available in our code. But this may be a governing parameter in design of our structures, especially when we are talking about zone 2 and 3. Interestingly, this site effect is more important in low seismicity areas. So in case of high seismicity areas, this amplification is not that predominant, because there the soil undergoes inelastic deformations and a lot of energy dissipation takes place within the soil, and such high amplification is not observed there. But here you see in case of Mexico City, which was 350 kilometers from the fault, that means it was having a much less severe intensity of the earthquake. There this phenomena was very significant. So there are some issues which are more relevant, and we have to be more cautious when we are designing our buildings on low seismicity areas like Bombay or Chennai or any other South Indian city. There this phenomena can be even more important. Now what we see in our code, all of us are familiar. This is the shape of the response spectrum. I am calling it a shape because it is not response spectrum. It is rather normalized shape of the response spectrum, and it has been normalized with respect to ZPA. And that's why this value corresponding to 0 period becomes 1. And it increases. The peak is at 2.5. So the peak spectral acceleration which we are expecting is 2.5 times the ZPA or the zone factor. And this continues up to different periods. In case of rock, it continues up to 0.4 second, then 0.6 second, and now in our code it has been increased. In the revised code I will show it has been increased up to 0.8 second. And after that it diminishes in proportional to 1/t up to 4 second. And beyond 4 second it is assumed to be constant. Now this portion 4 to 6 second, this is a problematic area, because most of our tall buildings, rather many of our tall buildings will be in this range. And in this range, the spectral acceleration is already very low. So even if we assume it to be constant, most of the times it will be the minimum base shear which is going to govern. So assuming constant acceleration does not affect the forces, but it will affect the displacement drastically. And it may be very difficult to satisfy the interstory drift limits when we are designing our buildings in this range of the period. This phenomena, this problem has been identified in the code, and after a few slides, I will show you the revised response spectrum in our code. And there it has been realized that actually it should not be constant, but rather it is varying proportional to 1 upon t square. So here the spectral acceleration reduces even faster, even at higher rate. And as a result, sorry, we get much smaller displacements as compared to what we will get when we are assuming this spectral acceleration to be constant. I have some throat infection, so please bear with me. Okay, so this is the new response spectrum. This is given in IS 1893 draft code, which is in wide circulation. And you can see here in this revision, this constant part has been recognized up to a period of 0.01 second. So those structures which are very rigid, having period less than 0.0 second, I mean, in our buildings, it is not of any significance because our buildings will have minimum period 0.1 second. And even if we are considering single story building, the period will be roughly 0.1 second. So this is not of much significance, but when we are doing modal analysis, then some of the higher modes may go in this range. So if we are having a higher mode, which is having frequency, usually we say 33 hertz, that gives 1 by 33 seconds. But our code recognizes this beyond 0.01, that means beyond 100 hertz. So actually this should have been up to 0.03 seconds. So those modes we consider as rigid modes, and the spectral acceleration we consider they are same as jet period. Then the constant period, the peak spectral acceleration period has been extended up to 0.8 second for the site class B. So in place of that earlier site classification, soil type 1, 2, 3, the revised code is having a site classification in line with the American code. That is based on VS30, the shear wave velocity in top 30 meters, the average shear wave velocity in top 30 meters. So site classes A, B, C, and D are identified. And for site class B, this continues up to 0.8 seconds. And then it is proportional to 1 upon t up to 6 seconds. And beyond 6 seconds, it is assumed proportional to 1 upon t square, and that continues up to 10 seconds. So there was a problem earlier in design of tall buildings. Many of our tall buildings were having period more than 6 seconds, and here the response spectrum was given up to 6 seconds only, so it was difficult. Now the code has been defined up to 10 seconds, so it will take care of most of our structures, including our tall buildings. So up to 10 seconds, the response spectrum has been made available, and from 6 seconds onwards, this is what we call constant displacement range. So the spectral acceleration is proportional to 1 upon t square, and if we convert this acceleration spectrum into displacement spectrum, then we will see that the displacement will go on increasing up to 6 seconds, and beyond 6 seconds it will become constant. So the displacement of those buildings which have period between 6 to 10 seconds, the displacement will be same. It will not depend on the period of the structure, if the period is between 6 to 10 seconds. So this is a new dimension added to the response spectrum in the revised code, or the code rather under revision. It is still in wide circulation. Then to obtain the EPGA or zero period acceleration or the response spectrum itself, there are two approaches. One is the deterministic seismic hazard assessment. Our current code is based on deterministic seismic hazard assessment. In deterministic seismic hazard assessment, we consider the characteristics of the sources So we consider all the sources in the vicinity of our structure, but we consider the characteristics of these sources deterministically. So we decide one magnitude of earthquake which can be caused, or the maximum magnitude of earthquake which can be caused by a given source. And then we consider all such sources and their distances from our site. And then we calculate the acceleration, ground acceleration, which will be caused, or the ground velocity or the ground displacement, which will be caused by different sources. And then we take an envelope of all of those, and that we call our design response spectrum, which is given in our code. So current code is based on deterministic seismic hazard assessment. And in deterministic seismic hazard assessment, as the name itself suggests, we get mean value and mean plus sigma. So mean and standard deviation we can get, but we do not get any return period. So there is no return period or probability of occurrence associated with DSHA. That we obtain from PSHA, probabilistic seismic hazard assessment. So in probabilistic seismic hazard assessment, we not only consider the magnitude of the earthquake, which will be caused by a particular source, a particular fault, but also the probability of occurrence. So in general, at any source, different magnitudes of earthquakes keep occurring. The smaller earthquakes occur very frequently. Those earthquakes which we can't even sense, that type of earthquakes are occurring on daily basis. And large earthquakes which repeat or which have severe damage potential, those repeat at much larger interval. Thousands of years is the interval at which those are repeating. So if we take into account that recurrence of the earthquake also, the probability or the rate at which those are occurring, then we can get an estimate of a earthquake along with its probability of occurrence. And this method is called probabilistic seismic hazard assessment. And our current, the revised code, the current code is based on DSHA. The revised code, for which I have shown you the shape of the response spectrum just now, that is based on PSHA. So the code invites circulation. There, the zone factors have been obtained based on PSHA. And as a result, those zone factors which have been obtained, those also have a frequency of occurrence or a return period associated with it. And sometimes, at least when we are using our current code, we have to relate the deterministic and probabilistic estimates of earthquake hazard. So ASC 7 explains that for the purpose of comparison, what we are getting from mean from the DSHA as mean plus 1 sigma, that can be considered corresponding to MC of the probabilistic seismic hazard assessment. I will explain these terms in this slide. So different, when we are doing a probabilistic seismic hazard assessment, we can estimate a probability of occurrence. And this probability of occurrence we define in terms of the lifespan of the structures. Generally, we take it as 50 years. So we can have 50% probability of occurrence of 50 years. This we call serviceability earthquake. So this is an important probability of occurrence for us because this is being recognized now by the code under revision as serviceability earthquake. So serviceability earthquake will be considered as the earthquake having 50% probability of occurrence in 50 years and the average return period of 72 years. So I will show you that our code also defines now the revised code or the code under revision, which is in wide circulation, that defines the serviceability earthquake also. Then we have this 10% probability of occurrence in 50 years. This is another important level of earthquake shaking, which we call design basis earthquake or DBE. Currently, most of the code in the world are designing for this level of earthquake, 475 years or roughly 500 years, we say. So with this 500 years return period earthquake, we are designing our structures. But this is not the largest earthquake which can come. Earthquakes with higher intensity but lesser probability of occurrence can occur. And there is an earthquake level which we define as 2% in 50 years, which is having a return period of 2000 475, roughly 2,500 years. We call this as maximum considered earthquake, MCE. And this is considered sort of a theoretical upper limit. So when we were doing deterministic seismic hazard assessment, then mean plus 1 sigma, that is 84 percentile. That corresponds to this level. And when we are doing probabilistic seismic hazard assessment, then 2% in 50 years. And when we are designing our buildings, our intended performance objective is that our building should not collapse at MC. So we have to understand that actually we are not designing for MC. We are designing for DVE, but we intend that our structure will not collapse under MC. And some people question this method of design also, and they suggest that if we want our buildings not to collapse at MC, we should design it for MC, of course, with adjusted response reduction factor. The response reduction factor will not be same as we are using currently for DVE. So currently we are designing with DVE, taking advantage of the inelastic energy dissipation due to ductility of the structure through response reduction factor R, and we intend that our building does not collapse under MC. It is quite complex story. And then this is also not the limit. Earthquakes even more severe than this can come. So 2% in 50 years is only a theoretical estimate of what we consider maximum considered earthquake. But in nature, even higher than this earthquake can also occur. And in case of some important structures, we may like to design, let us say, nuclear power station. Perhaps we will like to design for an earthquake even higher than this. So when we are designing our buildings for MC, even for MCE, in some cases like NDMA guidelines, those are talking about design for MCE, NDMA guidelines for design of hospitals. So though there the design is suggested for MCE, but we should not understand that that is the limit. Earthquakes higher than that can also occur, although the probability of occurrence is much lower. So sometimes there is a question that suppose I'm designing with response reduction factor R is equal to 1. Do I need to do ductile detailing? So why we are interested in ductile detailing, as we have discussed in some of our previous webinars and talks also, that earthquakes larger than DV can come, even up to MC can come, and even larger than MC can also come. So when an earthquake larger than what we have designed for is coming, then how the building is going to survive that earthquake? Where is the reserve strength? So reserve strength is available in ductility. So that's why the code says that in zone 3, 4, and 5, even if you are designing your structure as elastic, you have to follow ductile detailing, because ductile detailing is providing us the reserve strength, not the factor of safety. I will talk about that factor of safety which we are using in case of limit state design. So this is ASC 7 2016 version, and it defines that when we are comparing deterministic ground motions in terms of MCE, that is a concept of probabilistic seismic hazard assessment, then 84th percentile of 5% damped spectral response acceleration we can consider as MCE spectrum. So this 84 percentile is important. And if you go to the older ASC 7 version, 2005 version or the previous version, then in place of this 84 percentile, it has the same definition, but it is saying 150% of the mean. So this 150% or factor of 1.5, this is a very important factor which we have to understand. It is nothing but it is relating the DSHA results with the PSHA results. So DSHA results does not tell us what is DB or MC actually. The concept of DB or MC or probability of occurrence is there only in probabilistic seismic hazard assessment. But if I want to compare the two, I have to multiply a factor of 1.5. And this factor of 1.5 is used in our code in the load factor, which we are using in our limit state design. So it is only our code which is having a load factor of 1.5 for earthquake. So what is given in our code as the zone factor, the current code, the zone factor is given as the mean value obtained from DSH. And if I have to make it equivalent to MCE, I have to multiply it by 1.5. So what we have to understand is that the zone factor given in our current IS 1893 version is the median EPG. If I multiply this by 1.5, so 1.5 Z becomes the MCE or 84 percentile. And if I divide by 2, so 1.5 Z by 2, that is close to DVE. So that becomes DVE. And we are using this in our strength or ULS load limit state design. So we are using actually a factor of 1.5 over Z by 2. So this factor of 1.5 is actually a conversion factor. It is not a load factor. So this 1.5 is sort of a correction factor, which is converting the median value into 84 percentile, or what we are getting as median of DSHA, we convert that into MC. So this 1.5 is only to convert this in terms of MC and DV. It is not really a load factor. And that's why it is not existing in other codes. And interestingly, our code under wide circulation has also done away with this 1.5. So this factor of 1.5 is not there in the code to be revised also. And when we consider without this factor 1.5, just Z by 2, it is representing the serviceability earthquake, which is to be used in working stress design or serviceability limit state design when we are designing building or bridge. So if I have to get the DBE or MC or serviceability earthquake from our code, I have to take the shape which is given in the code and I have to multiply this. Actually, this shape also, this is also a misnomer, SA by G. Actually, it is SA by Z. As I told you that this is the shape of the response spectrum, which is normalized by the zero period acceleration ZPA or Z. So it is actually SA by Z. And that's why we have to multiply it by Z. So when we multiply it by 1.5 Z, then it becomes MCE. When we multiply it by 0.75 Z, that is 1.5 Z by 2, then it is corresponding to DVE. And when we multiply it by 0.5 Z, that is Z by 2, then it is serviceability. So this is the relationship of our current code response spectrum with respect to DVE, MC, and serviceability. And the load combinations, if we look at AC load combinations, so we can see here in AC load combinations, the load factor for earthquake is 1 because they are already using MC. So they need not to multiply it by 1.5. Whereas in our code, we are using mean value obtained from DSHA. So that's why we had to multiply by a factor of 1.5. And for allowable stress design or serviceability limit state, the load factor is 0.7. So we have to understand here this factor 1.7, it is nothing but 1 over 1.5 of this factor. So the relationship between serviceability earthquake and the DBE has been considered in American code also as 1 over 1.5, which is there in our code also. In our code, this relationship is just inverse of it. We consider 1 in serviceability earthquake and 1.5 in strength design. Whereas in other codes and also in our code in wide circulation, this relationship has been reversed. So in our current code, which is in wide circulation, rather future code, the limit state design or limit state of strength combinations are given like this. So you can see earlier it used to be 1.5 dead load plus 1.5 earthquake load. And here a subscript D has been added. I will just explain what this D means. So this is 1.5 dead load plus earthquake load. So you can see that the factor is now 1. There is no more a factor of 1.5. So this factor of 1.5, which is there in the current code, we have to understand it. We have to use it with caution. Then the other factor was 1.9 dead load plus 1.5 earthquake. So here also this factor 1.5 has been done up. And the limit state of serviceability, there is also factor 1, but this earthquake EES, the subscript S has been used, whereas here the D has been used. So this EED, yes, any issue? I hope everybody is able to hear me. I'm connected.
There is a complaint from many of the participants that they are not able to see the screen.
They are not able to see the screen.
In the sense, slides are not moving.
Slides are not moving.
Oh.
So what I will do, I will stop
You
sharing
stop
and
sharing,
share again.
yeah, and we can reshare it. Yeah.
I will reshare and let's see. I think this is a bandwidth problem. So what I will do, I will stop my video also. Are you able to see?
Yeah.
And I will stop my video. Then perhaps the slides will move. So please stop me when this happens again, because there is no point in just keep on talking without looking at the corresponding slide. So perhaps now you can see, and here we see that there is a subscript D and S. And this D subscript is actually representing the design earthquake for strength, and S is representing the serviceability earthquake. And which earthquake will be used for design, that is also specified in the code, which return period. So this is a table which I have just taken from that code under, I don't know how to go away with this. So you can see that normal structures, the strength design or that EED is based on 475. And that serviceability check is to be done for 73 years return period. So this is that serviceability definition, which we just now discussed, having 50% probability of occurrence in 50 years during the design life of the structure. So for normal structure, this is like this. For important structures, this 470 in place of 475 years, it has been increased to 975 years return period. So earlier we were doing this by applying an importance factor. So now in place of the importance factor, the code is proposing to increase the return period so that the structure will be designed for a higher level of earthquake. And accordingly, its serviceability check will also be carried out for 225 years. And in case of critical structures, and interestingly, hospital related structures, hospital buildings are in this category. So there is going to be a drastic change in design of hospitals as per this code, because the hospitals, it is proposed to be designed for 2,475 years return period. Currently, we are designing our hospitals with 475 years return period and an importance factor of 1.5. Now we will be designing it for 2,475 years return period, and the serviceability check shall be made for 475 years return period. So code has the code in circulation has now defined the return periods corresponding to EED and EES, and the zone factors are also defined with these return periods now. So the whole country now is divided into 5 zones. In contrast to the current 5 zones, starting from zone 2 to zone 5, now we have 5 zones starting from zone 2 to zone 6. And a new zone, zone 6 has been introduced, and you can see it is somewhat closer to zone 5. Whole of the Northeast, earlier it was in zone 5, so now it has been put in zone 6. And there is this belt in the central Himalayas region, which is put in zone 6, and the Bhuj area is put in zone 6. Then along with this zone 6, there is a zone 5. So this Indo-Gangetic plain, where we are having deep alluvium, that has been put in zone 5, and Delhi is still in zone 4. So this portion has been kept in zone 4. Mumbai is in zone 3 here, and a small portion here near Koina, where an earthquake has occurred. So this has been put in zone 5. And the zone factor for different zones is like this. So please understand that when we are comparing for 2475 years with the current code, then it has to be compared with a factor of 1.5. For example, the value of zone factor for zone 5 in the current code is 0.36. And if we have to convert it into equivalent 2475 years return period earthquake, then we have to multiply it by 1.5. So it is 0.54. So zone 5, currently it is 0.54, and what is proposed here is 0.6. So it is nearby, it is close. But zone 5 has been now changed. Where the zone 5 is currently, now we have zone 6 at those locations, and many locations which are currently in zone 4. So zone 4 is having a zone factor currently of 0.24. If we multiply that by 1.5, this becomes 0.36. So some of the portions in the Himalayas which were earlier, or let us say Bhuj, which were earlier in zone 4, I mean close to Bhuj. Bhuj was in zone 5, but some nearby areas which were earlier in zone 4, which were being designed for 0.36. In place of that, those will be designed for now 0.75. So this change is going to occur, and this is based on the probabilistic seismic hazard assessment exercise which has been conducted. So as a result of that probabilistic seismic hazard assessment, it has been estimated that the actual risk, actual hazard which is existing in these locations is much higher. And the table has been given with in terms of different return periods, so that with respect to the previous table here, you can find out what value of JAD you have to use from this table. So value of JAD now will depend from the category of the building to other category of the building. So you will decide the return period from that table, and corresponding to the return period for limit state design and the serviceability state design, you will read the zone factor. So that's about the hazard. Now, once we have decided zone factor and multiplied that by the shape of the response spectrum, we get the response spectrum. So we can design our structure for that response spectrum, or we can design for the ground motion itself. So some characteristics of the ground motion and response spectra I have discussed, but there are some other properties which I want to highlight here. So these are the three components of the same earthquake recorded at same location. And what we see that the components in the two horizontal directions are more or less of the same intensity. One component is of slightly lower intensity as compared to the other. Usually it happens when we are recording the earthquakes. One component may be stronger, the other component may be slightly weaker. But there is no distinct relationship. It will depend on the orientation in which the ground shaking is occurring. And what we see here that the two components are uncorrelated. Both are random. So when a pulse is occurring in, let us say, H1 direction, the pulse in H2 direction may be of much smaller intensity. So during earthquake, the ground shaking is not only changing its magnitude, it is also changing its direction. So at one instant of time, the acceleration is occurring in one direction, and another instant of time it is occurring in the other direction. And as a result, the relationship between the two components is also not constant. So there is no constant relationship between these two components. Their relationship, if I take a ratio of these two components or acceleration in the two directions, that is also varying randomly. So this is a very important relationship, and it also helps us in design, because when the peak earthquake force is occurring in one direction, the peak earthquake force in the other direction is not occurring. And that's why in our conventional design, we use 100% in one direction and 30% in the other direction. So statistically, it has been observed, actually it will vary from ground motion to ground motion. The relationship is not precisely 100:30. It will vary, but on an average, this relationship has been obtained that when the peak in one direction is occurring, the other direction is having on an average 30% of its peak. So that 130 combination rule we use. When we are doing time history analysis, usually we have to consider multiple components. Both the components we have to consider. So many times people make a mistake that they apply the same ground motion in both the directions. That becomes a perfectly correlated ground shaking. When peak in X direction is occurring, peak in Y direction is also occurring. So that is not to be done. The two components, if we are using in time history analysis, both the components should be independent. So those should be either the two components recorded from the same earthquake, which will be by nature, those will be non-correlated, independent, random vibrations, or we should generate those in such a way that these are independent, non-correlated to each other. And same is true in the vertical direction. So you can see in vertical direction also. And one more interesting thing you can find here, that in vertical direction, the frequency is larger. The time interval it is taking to cross the zero line is smaller. So frequency in vertical direction is higher. So generally in vertical direction, we are getting higher frequency. And here also, when the peak vertical acceleration is occurring, the peak in the two horizontal directions is not occurring simultaneously. So we take 100, 30, 30. And now the code in its combination has included the other direction also. So when we are looking, okay, I have not included that here, but if you look at white circulation draft, there you will see that now 100, 30, 30 combination has been given. That means horizontal and vertical both have been combined. And many times people ask that whether in which case we should consider the vertical acceleration. So please make it a habit to consider vertical acceleration in all the cases. In most of the cases, vertical acceleration will not cause any effect on our design. But wherever it will have an effect, it will be automatically taken into consideration. So it is a good practice to consider all the three components. When we are using response spectrum, we can combine them using 130-30 rule. When we are doing time history analysis, we can consider all the three components of the ground motions applied simultaneously to our structure. Now, this is the velocity time history of the same ground motions. So we can see that the velocity is also random and the peak is occurring in one direction. The peak is not occurring in the other direction. But if we look at the response spectra, so we can see that response spectra in the two horizontal directions are similar. Those are not going to be same, but those are similar in the shape. But the vertical response spectrum in vertical direction, you can see the peak is occurring at a very short period. So as you have seen from the plot itself, that the frequency in the vertical direction is higher, and that's why the peak is also occurring corresponding to higher frequency or shorter period in the vertical direction. So in general, the vertical direction peak is occurring at shorter periods. And in the two horizontal directions, the response spectrum can be considered to be the same, but the time history cannot be taken same. That should not be done, because in that case, the ground motion become correlated and the results will be excessively conservative. Then coming to these two methods, the types of analysis which we do, for that we have to understand the characteristics, dynamic characteristics of the building. So far we have talked about the dynamic characteristics of the ground motion. Now we will talk about what happens to the building. So any building, or for that matter any structure, can be considered as consisting of several modes, and these modes we call natural modes, and these can be obtained by performing eigen value solution of the stiffness and mass matrix, or what we call free vibration analysis of our building, and we get the different modes, period in different modes, and the mode shape. And these mode shapes, the typical shapes are here. So in case of first mode, all the masses along the height of the building, all the points along the height of the building will be vibrating in same direction. In case of second mode, half will be vibrating in one direction and half will be vibrating in the other direction, and so on. And as we go from lower mode to higher mode, actually these higher modes, their numbering is done based on the hierarchy of their, or the order of their frequency. So these are simply numbered in the order of increasing frequency. And increasing frequency means reducing period. So as the mode increases from 1 to 3, the period goes on reducing. And I have interpreted that by showing here shorter structures corresponding to shorter single degree of freedom systems corresponding to higher modes. So we can see as the height is reducing, the period is reducing, and the frequency is increasing. So these modes, we all are mostly familiar with this concept of the modes, and any structure can be represented by these modes, and these modes have certain properties which we call orthogonality. And because of that property, by virtue of that property, we can decompose the complex equation of motion of a vertical degree of freedom in terms of these simple structures. So rather than analyzing the full building, I can analyze these simple structures. And another advantage is that the response, the peak response of these simple structures is given directly in terms of response spectrum, because we discussed that response spectrum is nothing but the plot of the response of single degree freedom systems of different period. So here, if I know the period in different modes, the response corresponding to, or response of the single degree freedom system corresponding to that mode, I can get. And if I have to obtain the response of this actual structure, which is multi-degree freedom system, I have to simply obtain responses of individual single degree freedom systems, multiply those by these spectral shapes and the corresponding contribution factor, mode participation factor of different modes. I can get the response of the structure. This is one advantage. Using this, we can simplify the analysis of our structure. There is another advantage available from nature, and that is that the participation of these modes in the total response of the structure goes on reducing as the period goes on reducing. So initial modes, the first mode, or what we call also the fundamental mode, has the maximum participation, and the higher modes, as the frequency increases or the period reduces or the mode shapes become more and more complex, their participation goes on reducing. And generally, initial 5 to 10 or 12 modes provide us sufficiently accurate, and the code provides a limit that minimum number of modes we should consider, which provide 90% participation in the total mass of the building. So if we are having modal masses of corresponding to these modes, and we add that, and up to that mode for which we are getting 90% mass participation, and we take response corresponding to those modes and combine those, then I will get the response of the building quite accurately, response of this structure quite accurately. So what we do, we first have to obtain these mode shapes and the corresponding frequencies. Now, you might have seen in some literature, as well as some of you may be even using, that two options are available in the software. One is the eigenvector, another is the Ritz vector. So we can perform this modal decomposition or modal analysis using with any of these two options. In fact, more number of or more types of vectors are available. For decomposition, we are utilizing one characteristics of these sets of vectors, either eigenvectors or Ritz vectors, and that characteristic is that these are orthogonal to each other. So eigenvectors are also a set which has vectors orthogonal to each other, and Ritz vector is also another similar set which is also having vectors orthogonal to each other, and we can utilize both to perform modal analysis. But eigenvectors have an advantage that these are representing physical properties of the building, and those physical properties are the frequencies and mode shapes in different natural modes, or what we call free vibration characteristics of the building. So this is eigenvector which is providing us the free vibration characteristics of the building, not the Ritz vector. In some cases, Ritz vector can also lead us to the same vector as the eigenvectors. That's a different story. But it is eigenvector which will provide us the frequencies and mode shape and not the Ritz vector. Ritz vector are actually load dependent, and in some cases, these can give us better convergence. A fewer number of Ritz vectors can give us larger mass participation. So what is suggested is that we should always start with eigenvectors, look at the eigenvectors, because eigenvectors not only help us in simplifying the mathematical solution of the problem, but these also provide a lot of information about physical behavior of the structure. So if we have made a mistake in modeling, that can also be indication of that is also available from the eigenvectors. So eigenvectors gives us a lot of physical information. That's why we should start with eigenvectors. But in some cases, if eigenvectors are not able to give us sufficient mass participation, that is 90%, even with large number of eigenvectors, we can try Ritz vectors. So in case of some complex structures, we can go for that. For example, in buildings, generally we get good participation using eigenvectors also. But in some structures like bridges, it may be possible that Ritz vector may give us better mass participation. So we can try Ritz vectors. So as far as the solution is concerned, both are acceptable. You can use any of the two, whichever serves your purpose. But for the physical understanding, it is important that we do eigen solution also and look at the eigenvectors, mode shapes, and the frequencies. That will give us a lot of information, a lot of physical understanding about the behavior of the structure. Then, when eigenvectors are not giving us sufficient mass participation, we can go for Ritz vectors. In some cases, Ritz vector can provide a better participation factor, and it will require to use a smaller number of modes, and hence it can make our analysis faster. And that's why some of the softwares, they recommend using of Ritz vector in every case. It can be done. There is no problem with that. But in addition to that, it is important to do eigenvector solution also and look at the eigenvectors, that those are reasonable or not. Then different types of analysis depending on how many modes we are considering. So if we are considering single mode, then we can obtain a good estimate. Of course, this is an approximation. Any structure is consisting of several modes. We are considering here only one mode. So if I assume that whole of the mass of the building is participating in the first mode itself, so I can read the spectral acceleration from the response spectrum corresponding to the first period. I will get that value of spectral acceleration, and then I can calculate base shear corresponding to that. This method we call equivalent static analysis. So equivalent static analysis is nothing but the single mode analysis. We are assuming that whole of the mass of the building is participating in single mode, that is first mode, and the response we can get directly from the response spectrum. Generally, this is a conservative method because we are assuming that whole of the mass is participating in the first mode. So we will get a conservative results, but in some cases it may be non-conservative as well. Then we have what we call response history analysis. So in response history analysis, either we can analyze our building as a whole subjected to the ground motion, but in place of that, what we can do is we can analyze individual single degree freedom systems corresponding to each mode subjected to the same ground motion for which we want to analyze our buildings. And then we can get the response of each single degree freedom system. Now, response of this each single degree freedom system we can add directly. Okay. Only thing is we have to keep in mind that a single degree freedom system will give us one response, whereas in a multi-story building, there will be response. We need the response at every story. So the response at every story can be obtained by multiplying this response of the single degree freedom system by the corresponding mode shape. So this response we multiply by the corresponding mode shape and also the corresponding mode participation factor. and then we add it. So we will get the response of the building. Now, alternative to this, we can obtain the response of the building directly. That is what we call the direct response history analysis or direct time history analysis. So time history analysis can be done in two ways. Either the equation of motion can be solved directly. So those who are familiar a little bit with the mathematics behind the vibrations of a multi-story building, they know that we are getting coupled equations, which are represented in terms of matrices. So we can solve that coupled equation directly, the coupled equation of motion or the coupled differential equation directly in terms of matrices. Then it is called direct time history analysis, and that will be the most accurate analysis. Alternatively, we can simplify this and we can reduce the computational time significantly. We can perform analysis of single degree freedom systems, which takes much less time, to the same ground motion, and then we can combine the response of the single degree freedom systems by multiplying with the corresponding spectral shape. So this method, the modal response history analysis method. So we have direct response history analysis as well as modal response history analysis. Modal response history analysis is commonly used because this is much faster than the direct response history analysis. Alternatively, rather than doing time history analysis, because even if we have to do time history analysis of a single degree freedom system, it takes computer time. We can simplify even further. So rather than performing the response performing the analysis of the single degree freedom system, we can read the peak response of the single degree freedom system directly from the response spectrum. So this single degree freedom system response we will get from the same response spectrum for which we want to perform the analysis of the building. And we have to keep in mind that the response spectrum is giving us the peak response, whereas here we were getting the full time history of the response of the single degree freedom system. And you can understand that the peak response of each single degree freedom system is not occurring simultaneously because their periods are different. And when their periods are different, they will be vibrating differently. And the peak responses will be occurring at different time instants. So we should not add them directly. We can add the full time history directly, then there is no problem. But when we are having only peak responses cannot be added directly. And that's why we have to use SRSS and CQC method, because using response spectrum, we are getting the peak response. The most accurate method, as I just discussed, that we make a multi-degree freedom model of our building, analyze it directly. We call it direct time history analysis. All the modes here are inherently considered. So we need not to worry that how many modes we need, because sometimes in some of the structures, it will not be possible to get 90% mass participation, especially when we will talk about the buildings with basements. It will not be possible to excite 90% mass. Or if we want to get that, we will need very large number of modes, and some of those modes may be rigid. So you may not even be able to solve that. So possibility of getting 90% mass participation may be difficult. So in such cases, we can go for direct time history analysis. And no approximation is involved here. We are considering all the modes, and this is the most rigorous and sophisticated analysis. The problem is how to get the time histories, because this will require time history, whereas the code is giving us only the response spectrum. So this question is always there, that whether we should use response spectrum analysis or time history analysis. So it is not necessary. Let me tell you, it is not necessary to perform time history analysis. Response spectrum analysis is also accurate. It is quite accurate method. Only one condition is there, that we have the adequate number of modes. So if we are able to identify adequate number of modes having more than 90% mass participation, either using eigenvector solution or using Ritz vector solution. So any of the two methods we can utilize. If we can achieve 90% mass participation, the response spectrum method is good enough. It will serve our purpose. But in some cases, like irregular buildings, buildings in which we want to consider soil structure interaction, including wave propagation, we need to perform time history analysis, because it may not be possible to have 90% mass participation. So there we have to go for time history analysis. And in case of response spectrum, we have to use 100:30 combination, whereas in case of time history analysis, you will apply two orthogonal components simultaneously, and generally the vertical component also should be used simultaneously, and this combination 100:30 combination etc. will be taken care of. And it is to be kept in mind that one response spectrum which is given in the code is enough for the design, but one set of time history is not enough. I mean, one time history having 3 records is not enough. We have to have multiple. We have to use multiple time histories. If we are using spectrum compatible time histories, then 3 sets are enough. And in case of linear time history analysis, and currently in this today's talk, we are limiting to linear time history analysis only, the 3 sets are okay. But when we are doing nonlinear time history analysis, 11 sets of recorded accelegrams are to be used. In nonlinear analysis, spectrum compatible time histories are not recommended. But in case of linear time history analysis, spectrum compatible time histories are good enough. Rather, spectrum compatible time histories only should be used. And 3 sets of just set of 3 ground motions of spectrum compatible nature are good enough. In case of buildings which are having special seismic devices like base isolation or dampers, we have to go for nonlinear time history analysis, or at least the equivalent linear time history analysis. In equivalent linear time history analysis, we can perform iterative linear time history analysis. And what we do, because we have a nonlinear load displacement behavior, so we will assume certain displacement in our device, and we will calculate secant stiffness corresponding to that period, that displacement, and then using that stiffness, we will perform the linear analysis and check at the end of the analysis whether the assumed displacement was close enough to the displacement which we have obtained after the analysis. If not, it has to be revised and iterations are to be performed. Now, as I said, that the major problem in case of time history analysis is selection of ground motions. How to get the ground motions? So there are 3 types of ground motions available. One is the recorded accelerogram. So we can get from the records of the past earthquakes. A number of websites are there where different records for past earthquakes are available. I have a list of those I will share with you. Then we have simulated accelegrams using the physical phenomena of source and path mechanism. People are trying to generate the accelegrams, although it is not very successful. We do not get simulated accelegrams which have the characteristics similar to the natural recorded accelegrams are not there. So still it is not very popular. Or we can have totally artificial accelegrams. So in artificial accelegrams, we just consider the response spectrum and an envelope like the one shown here that shows an increasing period, the period in which the ground motion is building up, then a more or less constant ground motion period, and then the period, the time period in which the ground motion is reducing and reaching to 0. So this envelope function and the response spectrum can be provided, and there are software which can generate artificial accelegrams. So either these artificial accelegrams can be used, or we can have recorded accelegrams and we can modify those in such a way that their spectrum matches with the target spectrum which we are going to design. So for example, here this dotted one is showing the response spectrum of a ground motion, a recorded ground motion, after performing a process what we call spectral matching. So software are now available using which you can do the spectral matching. So a preferable way is that we try to get a recorded accelerogram which is closest to our response spectrum, and at the same time it is also having the similar source conditions and the site conditions, and then we do a spectral matching of it and try to get or try to modify the ground motion in such a way that its response spectrum is very close to the response spectrum which we want to use for design. So there are advantages and disadvantages. Definitely the realistic recorded ground motions are very good, but only problem is that such ground motions are not always available. If you are lucky, you can get the ground motions which are very close to the response spectrum you are trying to select the ground motions for, but generally these will not be available, and in that case we have to go for spectrum compatible or synthesized ground motions. Now, how do we scale the ground motion? That can also be understood from here. So one way of scaling ground motion is that we match the PGA. So when we are matching the PGA, we can understand here that the smooth one, this is our target response spectrum, the design response spectrum, which we have constructed using the code guidelines. And then this is the response, red one is the response spectrum of the ground motion. And I match the PG of the two. So what I'm going to get is that this value here, this EPG, this will match. But we can see that actually in the rest of the period range, the response spectrum is far away from the target response spectrum. And if I try to compare it, or if I try to scale it in such a way that it is close to the target response spectrum, we can see that there is a large difference in PGA. So what I want to make the point about here is that PGA is not a good scaling factor. We should not scale the ground motions with respect to PGA, because matching the PGA doesn't mean that the response spectrum has matched. And at the period of your building, the two spectra may be very different. So PGA matching is not an acceptable method of matching the ground motions. On the other hand, I can use the spectral acceleration corresponding to the period of the building. So this T1 is the fundamental period of the building. I get the spectral acceleration of the time history as well as the target spectral acceleration at the same period. And then I scale the ground motion by the same factor, the factor of these two. So when I am scaling the ground motion by the same factor, the whole ground motion is multiplied by a constant factor, then the response spectrum will also be multiplied by the same factor. And in that case, the response spectrum will match here. But again, it is not necessary that you will get as good match as is shown in this figure. The response spectrum at other points may be either far below or far above the target response spectrum. So just matching at the one point is also not going to serve the purpose. So what we have to do, we have to do spectral matching or scaling in a range, in a period range. And what should be that period range? That period range should be slightly higher than the fundamental period and up to slightly shorter than that mode, which is giving us 90% mass participation. So we should find out a range in which I am getting 90% mass participation, multiply that by or increase that by 20% in both the directions. So 0.8 times the lower time period and 1.2 times the longer period. So longer period is the longest period of the building, that is the fundamental period of the building. And fundamental period of the building again in the two directions may be different. In X and Y directions, the period may be different. So we have to consider the longest fundamental period, multiply that by 1.2. That is the upper range of the period, and 0.8 times that period, which is giving us 90% mass participation in the building in both the directions. In this range, we should try to match our response spectrum. One example I am showing here after spectral matching at one period. So we can see here 30 ground motions are given. The original response spectra are shown here. Then I have chosen a period of interest as 1 second, and then these have been scaled with respect to the period at 1 second. So all these ground motions have now the same spectral acceleration at one period, but you can see away from 1 period, 1 second period, you can see that there is large variation. And this variation we have to keep in mind. So either we have to reduce this variation by doing spectral matching, or we have to consider sufficient number of ground motions, and mean and standard deviation of those ground motions is to be considered while making a decision regarding the design. So as I said that there are a number of strong motion databases from where you can get the records. In India, our department is managing this last website, Esmos. You can register here and then you can download the time histories. You will get the time histories which have been recorded in India. The most important one is this Shear, NG West 2, Berkeley University maintains this. So most of the ground motions you will get here, and not only that, they have a very good search engine in which you can just specify the period, and the website itself will search and provide you the ground motions which are matching with your criteria. So you can specify the response spectrum, you can specify the magnitude range in which you are looking for, the distance, even the site type, or shear wave velocity BS30 at your site. And then the website, the search engine of the website has been designed in such a way that it will provide you the ground motions having best match with your search. So most commonly used website is this Shear. Then there are software tools which can help you in matching the ground motions with a target response spectrum. Some are available in open domain, public domain. Some are proprietary also. Seismomatch provides a student or teaching version and a commercial version. So commercial version you can have much better fit, whereas in a student version there is a limit how close you can do spectral matching of your ground motions, but you can download this from this these web links and use it. So there are software tools. One spectral matching tool has been prepared by Professor Gupta at IIT Kanpur. Bldgs, this is also a sophisticated tool. This is available in public domain. Only thing is that this is a command based. You will not get GUI of this, but you can use, especially who want to use for research purpose, they can use this tool also for the purpose of spectral matching. So this is about the response spectrum and time history matching. Time history analysis of tall buildings. Now I want to take up some modeling issues because still I have time. Can I continue for another half an hour? Kulkarni sir?
Yes, you can. Yeah.
Okay. So I just want to discuss some very common issues which are troubling our designers and what to do about those. So one problem is how to perform analysis of buildings with basement and podium. So in case of the buildings with basement and podium, generally the stiffness of the basement and podium is higher, whereas the tower stiffness is less. Further, with same basement, multiple towers may be arising. So in such case, what should we do? So if we try to perform the analysis of the system as a whole, that is also possible. We call it single stage analysis, but single stage analysis, the problem is that it is difficult to excite the bottom rigid portion. So you have to consider either a large number of modes so that 90% mass participation you get. If you are not able to do that, you have to do a direct time history analysis. In direct time history analysis, we analyze the full model by applying the ground motion at its base, and all the modes are inherently considered in this analysis. Otherwise, if we are doing modal analysis, we have to ensure that those modes which are participating, which are contributing within 90% mass participation, all those modes should be considered. Now, two types of analysis are possible here. In one case, we can model the tower and the basement together, and we can apply the ground motion at the base of this basement. We are not considering soil, effect of soil here at all. Although the basement is inside the soil, but we are considering that the ground motion is applied at the base of the basement at the foundation level, and the soil surrounding is ignored in this analysis. Effect of the soil, however, is to be considered while designing the retaining walls of the basement. And we have to consider both static pressure as well as dynamic earth pressure. So static earth pressure we can get if this type of structure is there where the retaining walls are part of the structural system itself. That means the top of the retaining walls is also connected to the floors. In that case, we have to consider the pressure at rest. But if this wall is cantilevered, it is not connected to the structural system, it is not part of the structural system, then this will be considered, or this will be designed for active earth pressure. And then the dynamic component of the earth pressure will also be calculated using Monod-Navier rule, and we have to design the shear walls for both. So effect of the soil will be considered in designing the retaining walls. Otherwise, while performing the analysis, we can ignore that, but we have to model the basement. The rigid walls of the basement, we will model here. If we want to consider, this is more accurate analysis, but not always necessary to go for this, what we call rigid bathtub analysis, where we are considering the effect of the soil also through these springs, or sometimes springs and dampers. So if we want to consider the flexibility of the soil, then we can represent it only by springs. If we want to consider the effect of the damping also, we can do spring and damper modeling. AC7 provides this. If anybody is interested in doing this type of modeling, we can follow AC7, and there are other documents also which provide how to get the stiffness of these springs. So we made this model, and at the end, what is shown here by this rigid bathtub, actually it is notional. What we are doing, the other ends of these springs will be grounded, and the same acceleration will be applied at the grounded end of all these springs. So this is only to represent that the same acceleration, the same ground motion, we are going to apply at the ends of all these soil springs. That this has been shown. So actually what we are doing, we are supporting our basement on these springs, and at the end of these springs, we will apply the ground motions, the same ground motion which we have applied at the base of the basement earlier in the previous model. But this B model is also quite accurate. This is usually considered to be adequate. But problem here is, as I explained earlier also, that it may be difficult to mobilize the mass of the basement. And especially if the building is having several stories in basement, the mass in the basement may be significant, and it may be difficult to achieve 90% mass participation with reasonable number of modes. In that case, we can go for two-stage analysis. In two-stage analysis, the tower portion is analyzed separately, and the basement portion is analyzed separately. And the tower portion, we can perform dynamic analysis, either using response spectrum or time history. We can perform a separate analysis for the tower, assuming the tower to be fixed at the top of the basement or the podium. So the tower portion can be analyzed separately, and the basement portion can be analyzed separately. The analysis of the basement will be done using equivalent static method. Here we will use a static method, and because it is rigid, so depending on in what period range we are getting the period of vibration of the basement, we will read the value which will be either equal to Z or 2.5 Z or somewhere in between. Most of the cases it will be very rigid. The period of vibration of the basement will be less than 33 Hertz. In that case, we can simply use the value at EPG, at 0 period. That value of SA we can use. But for this method to be valid, there are certain conditions. This method can be analyzed only if the stiffness of the lower portion is much higher, at least 10 times the stiffness of the upper portion. Suppose we have a building with podium, and the podium is not having any shear wall, it is just having some columns, only the size is increased, then its stiffness is not increased. And in that case, this two-stage analysis will not be valid. Mostly it will be valid when we are analyzing buildings with basement. So because of the retaining walls, which are also acting as shear walls, the basement portion will be very rigid. In that case, we can go for this two-stage analysis, where the top portion can be analyzed separately using dynamic analysis, and base shear correction will also be made in the top portion. So sometimes people are also confused that where should they consider base for performing base shear correction, BB bar by BB correction. So in this case, the base shear correction will be applied at the top of the basement. And then the analysis for the basement will be performed under the base shear being, or the forces, base shear as well as overturning moment being transferred by the tower, and then the forces applied due to the inertia of the basement itself, which we can obtain using equivalent static analysis. So we will apply both these forces statically, and then we will perform design of the basement. In addition to these, we have to apply the soil pressure on our retaining walls. Now, another issue is how we should model shear walls, and how we should consider the forces in the shear wall in design. So two types of models, both are equally acceptable, are available for modeling of shear walls. One is the equivalent frame model, or what we call wide column model. So here the shear wall, if it is a planar shear wall, it can be represented by a single column, and that column will be assigned the section of the shear wall. If it is a non-planar shear wall, let us say in this case it is a C-shape or U-shape shear wall, that can also be represented by, or that can also be analyzed using wide column or the equivalent frame model. So here each of the flanges will be represented by separate columns, and the web will be represented by a separate column. And these will be interconnected through these rigid arms. So when we are representing or we are modeling a shear wall using a wide column, then it will be represented by a line along the centroid of the shear wall. But the width of the shear wall, that needs to be considered in our model, and that we will consider by providing rigid members in the horizontal direction, or we can use offset command wherever applicable. In case of non-planar shear walls, we can still use wide columns, but these columns needs to be interconnected through these rigid arms in each direction. Alternatively, we can use finite element. It is it is easier to visualize. So the shear wall looks like its own original geometric shape, whereas in equivalent frame method, the shape of the model was not resembling with the actual shape of the shear wall. Here in the advantage of the finite element method and the appeal, why it appeals our structural engineers is that the shape of the shear wall is retained. But we have to understand that the finite element method provides us stresses or stress resultants, bending moment and shear force also when we are obtaining. It provides those stress resultants also at points. So it is giving a variation of the stresses. So before design, because when we are performing RCC design is based on section. RCC design is not based upon the distribution of the stresses. Rather, it considers the stress resultants acting on a section. So the shear force, bending moment, axial force acting on a section is to be considered. So when we are designing our shear walls, it is very important that we consider the section, or we integrate the forces on a section. For example, if I have to design this C-shaped shear wall, and I have analyzed it using finite element, I have modeled using it finite element. After analysis, I will get distribution of bending moment and shear force. I have to integrate all of this bending moment, shear force, and axial force over the whole section So again, people make a mistake that they consider different walls as different piers. So they define flanges separately, web separately, and web separately and flanges separately. That is also not the correct method. The full section, which is going to act as a whole during earthquake or any other loading, the full section needs to be designed. So we will integrate the forces over the whole section, and this whole C-shaped section will be designed. Now, as I said, that if you don't want to go into that interpretation problem, then we can represent the buildings using equivalent frame. For example, here, this is a core, and it is a three-dimensional system, but we can still, the whole system can be represented just by two columns. So this C-shaped wall can be represented by one column. This C-shaped wall can be represented by the other column. And these coupling beams in between, these can be modeled separately. So even this type of shear wall can be represented by two columns or a 6-column model. What is 6-column model? Both the flanges will be represented, both the backs will be represented by individual columns. All the 4 flanges will be represented by 4 columns. And these will be interconnected wherever these are connected by shear walls, these will be interconnected by rigid beams. And wherever these are connected by coupling beams, then actual coupling beams will be used. So we can see here a rigid arm is connecting the column. Either this column is representing the flange, or this column may also represent the whole C-shaped wall. I can lump in one column. That is also possible. And when we are lumping this whole C-shaped wall in one column, I will get the total bending moment, shear force, and axial force on this C-shaped wall. When I'm doing finite element modeling, then also I have to finally obtain the bending moment, shear force, and axial force on the whole section by integrating, and softwares provide that facility how to integrate the forces over a section. Then there are some more issues in design and detailing of shear walls. There are some limitations of our current code. I want to highlight that also. So here we have to understand how the bending moment of a shear wall changes during earthquake. So when the earthquake level is low, the shear wall is behaving more or less linearly. Then the bending moment diagram is like that of a cantilever. The shear wall will behave like a cantilever, and the bending moment diagram will be like this. But as the intensity of earthquake increases, then the shear wall will yield at the base. Where we are having the maximum moment, the yielding will occur. So it yields at the base. And if the intensity increases further, so yielding at the base has increased, and when the yielding at the base occurs, the boundary conditions of the shear wall change, and the bending moment along the mid height starts increasing. So you can see that initially the shape was linear. Now the shape goes on changing, and the maximum bending moment tries to occur along the mid height, at the mid height of the shear wall. Now when we are designing shear wall, either we have to recognize that the flexural hinge can form at mid height also. That is one possibility, that we recognize this, that where our second hinge is going to form. Of course, the first hinge will form at the base, then a second hinge may form here. And in that case, we have to do ductile detailing here also. Alternatively, we limit our ductile detailing at the base, but we ensure that the plastic hinge does not form here. And to ensure that, we have to do capacity design. Now, capacity design of the shear walls is not given in our code at the moment. We have to refer to ACI 318. So I have taken this figure from ACI 318, and ACI 318 suggests that when we are designing a shear wall, its moment envelope has also to be amplified, and the shear envelope has to be amplified, and the factors by which the moment and shear envelope has to be specific, has to be enhanced, has to be amplified. Those are also given in the code. ACI 318 provides these factors. We can follow those. But what Mohile has suggested, that even that is not adequate. So this moment envelope, which is given in ACI 318, That is also not adequate. And what should be done? The moment at the base, whatever we are getting after amplification using ACY 318, that should be continued up to a critical height. And after that, it should be reduced, and our shear wall should be designed for this moment envelope. Then only we can ensure that the plastic hinge will form at the base and plastic hinge will not form in the middle. Otherwise, what will happen? If we are not designing for this increased moment, then first our shear wall is going to yield here, and then it will yield somewhere near the mid height. And when it is yielding at the mid height, we have to ensure that sufficient ductility, there should not be any brittle failure under the yielding near the mid height. So we have to ensure that ductile detailing is there throughout the height, or at least near the hinge where we are expecting the hinge to form at the mid height. Then another common confusion is regarding the boundary elements. Whether we have to provide boundary elements, and if we have to provide boundary elements, what should be the extent of the boundary elements? And in boundary elements, do I need to confine the reinforcement? Do I have to concentrate the reinforcement? I have to provide more reinforcement, or I can continue the same reinforcement and then I can confine at the ends. So again, for this also we have to understand the theory behind it, what is actually happening. So when a shear wall is subjected to lateral force and it is yielding near the base, and here the cracking pattern of two shear walls is given. In case of one shear wall, the reinforcement is concentrated. Higher reinforcement is provided near the boundary. Whereas in the other case, the same reinforcement which is provided in the rest of the shear wall, and we know the minimum reinforcement in the shear wall is much less, 0.25%, whereas this concentrated reinforcement, this is controlled by the column minimum reinforcement, that is 0.8%. So if we are providing minimum 0.8% reinforcement along the boundary, or we are providing 0.25% reinforcement here, the cracking pattern is very different. In case of this lower reinforcement, a single crack occurs. Whereas in case of this higher reinforcement, minimum 0.8%, the distributed cracking occurs. And as a result, the ductility which is available in this case, the ultimate curvature which is available in this case is much larger as compared to this. And the ductility which we are getting here is larger. So this concentration of longitudinal reinforcement near the boundary, or providing boundary elements with minimum reinforcement of 0.8% in the region in which, or in the height of the shear wall in which we expect the yielding to occur, is important. This should be provided. So let's make a practice that in all the cases we should provide, in the lower portion of the shear wall, we should provide boundary elements. Now these boundary elements, ACI 318 provides this guideline regarding what should be the extent of this concentration. So it is 0.15 times LW, 15% of the length of the shear wall. Here we should provide the concentration. And we can see that this is different than the confinement. This is concentration of the reinforcement, longitudinal reinforcement. Longitudinal reinforcement not less than 0.8%. That length is 0.15 LW. The confinement is coming from a different criteria. The confinement is based on the strain. So for example, our IS 13920, it says that the confinement, when our code is talking about the boundary element, it is talking about the confinement, and it is coming from the stress which we are getting on uncracked section. So we calculate the stress on uncracked section, and if it is more than 0.2 FCK, we have to provide confinement. So confinement we have to provide in all that concrete which will be subjected to a strain more than 0.0035, because unconfined concrete can take a strain of maximum up to 0.0035. After that it will fall. But during earthquake, the concrete is subjected to much larger strain, up to 2%. So all that portion of the concrete which will be subjected to strains higher than 0.0035 should be confined. Now, how to identify that portion? which will be subjected to strain larger than 0.0035. Code has given a simpler approach, a simple approach for that, that we will perform analysis of the building, assuming the section to be integral. We will not consider any cracking. And considering whole section, the gross section, we will calculate the stresses using simply P by A plus minus M by Z. And wherever the stresses are exceeding 0.2 FCK on compression side, that portion will be confined. So in that case, we will provide the confinement, and the extent of the confinement towards the neutral axis will be till we are having a 0.15 FCK stress. Actually, in our code, there is little ambiguity here. Our code is saying that it should be discontinued when stress decreases to 0.15 FCK. So it looks like that the code is talking about the height, that along the height where the boundary element is to be discontinued. But if we look at the corresponding clause in ACI 318, then it will be clear. It says that the boundary element is to be provided when stress exceeds 0.2 FC dash, and the depth of the boundary element should be kept until stress drops to 0.15 FC dash. So one thing is this is 0.15 FC dash. Our code has taken these values from here, but FC dash has been replaced by FCK, and we know FCK is slightly higher. So actually it should have been 0.15 into 0.8, that is 0.12 FCK. So wherever we are getting or up to that level or up to that distance from the neutral axis, where the stress is becoming 0.12 FCK, we should provide confinement. And in 15% of the length, we should provide concentration of the reinforcement. Generally, the concentration of the reinforcement and confining of the concrete will be put together. So both the requirements of the boundary element can be satisfied if we take larger of the two. So larger of the two will be wherever either the stress is becoming 0.12 FCK or 15% of the length, whichever is longer, that should be the length of the boundary element. And regarding the detailing of the boundary elements, I think our designers are clear. There is not much confusion. It is to be detailed as per code requirement for column. So the minimum reinforcement will be 0.8%, and the confining reinforcement we will calculate using column requirements. Another problem which we are facing and we do not get sufficient guidelines, especially when we are talking about MI1 type of construction, where the boundary is where the walls are quite long and the stresses may come out to be less, and people may not provide confining reinforcement and concentration of the reinforcement. There the crushing of the concrete can occur. So wherever this crushing of the concrete is occurring, we have to provide adequate confinement. So even when we are using long, thin, lightly reinforced shear walls, providing this boundary elements in the 15% of the length at each end is important. So there we should provide this confinement. Then another problem is thickness of the shear wall. Especially again in my one type of construction, we are providing very thin shear walls. And it has been observed during past earthquakes. In fact, this photo is from Christchurch earthquake. I have taken from Modal's book. So there the shear wall has buckled as a whole. And when the shear wall is buckling as a whole, it will lose its moment carrying capacity. So a minimum thickness has to be used. So Modal has provided this chart where he has compared the different requirements, and it depends. The minimum thickness will depend upon the strain which we are getting in the steel. So epsilon SM is the maximum strain in steel. So whatever maximum strain in the steel will be occurring during earthquake, and you can see that this strain is much larger. So this is 2%, 4%, 6% of that order. So that type of strain will occur. Generally, we do not allow a strain more than 5% in steel. So because the earthquake is cyclic in nature, so there is a phenomena of low cycle fatigue. So the maximum strain which we are permitting in steel in tension is 5%. So this is the range in which we will be having. And based on this range, different suggestions have been made. what Mohile has suggested, that the shear walls should have HU by B less than 10 within the hinge region and HU by B less than 16 elsewhere. So at least in the lower portion, lower few stories, the aspect ratio, that is height, story height to the thickness of the shear wall, that should be less than 10. That means if we are using a story height of, let us say, 3 meter, the minimum thickness should be 300 millimeter as per this clause. In the region in which we are expecting the plastic hinge to occur. And the top portion, it can go up to 200 millimeter. Eurocode specifies 200 millimeter, and our code specifies 150 millimeter and 300 millimeter for buildings with shear wall. So this 150 millimeter is already on lower side. If we compare it with the other recommendations, 150 millimeter is on lower side, and sometimes people are providing shear walls even thinner than this. So that type of the shear walls cannot be considered as a structural shear walls. At least our structural shear wall should have adequate thickness and boundary elements. Invariably, in the lower portions, we should provide the boundary elements. Then there are some very small detailing related problems which we make and which leads to catastrophic type of failure in case of shear wall. So in case of shear wall, very high shear force is attracted by the shear wall and it is transferred to the ground. And here, initially the failure was initiated by flexion and crushing of the concrete. And then later on, the failure occurred due to shear. And this failure was actually occurring because of the slip of the horizontal reinforcement, which our code does not give any attention in the detailing requirements. But ACI 318 has this recommendation that the horizontal reinforcement needs to be anchored properly into the confined core region. So if we are keeping the horizontal bars straight, then it should be anchored up to LD in the confined core, in the boundary element. It should go up to LD. If we are making a hook, then also if this LD is not available, this much length is not available, then we should make a hook here and ensure that this is not going to slip, because under shear, this horizontal reinforcement will be subjected to its maximum capacity, that is yielding, and the anchorage length should be adequate so that this reinforcement does not slip before getting rupture. Then out of plane bending of shear walls is another issue, whether we should consider out of plane bending in shear walls or not. And people generally quote that the shear walls are planar elements. We design these for planar elements. So if the shear walls or a shear wall building is properly proportioned, we are not connecting beams perpendicular to the shear walls, and we have adequate number of shear walls in both the directions. The bending moment which we will get from analysis in shear walls in out of plane direction will be very small, which can be ignored. But it is not that the shear wall should not be designed for out of plane bending moment. Shear wall should also be designed for biaxial moment in the same way as we design columns, especially when we are having beams connected perpendicular to the shear wall like this. So when we have beams connected to the shear walls perpendicular to perpendicular to its plane, then the shear wall will be subjected to large out of plane moments also. And whatever moments in out of plane we are getting from our analysis, shear wall needs to be designed for that. Then there are other issues regarding the connection of the beam or anchorage of the reinforcement of this beam perpendicular to the shear wall into the shear wall, because wherever the beam is crossing another column or shear wall, the embedment in the joint should be 20 times the diameter. So 20 times diameter should be the thickness of the shear wall. Shear wall may not have that much thickness. So in that case, we have to make certain arrangement of the beams. So these beams are integrated beams with the shear wall, or the cross section of the shear wall, I will rather put it like this, that the cross section of the shear wall is to be modified in such a way that this requirement of 20 times diameter is satisfied. And the shear wall is designed for biaxial moment, and it can be designed using section designer in the same way as we are designing our columns for biaxial movements. Then sometimes another problem is regarding the coupling beams. So sometimes the RCC coupling beams may not be adequate, and we have to provide either composite beams or steel beams. So it is an acceptable practice now that we use coupling beams made of steel, and in fact it has advantage because steel is having more ductility and steel is more ductile in shear. So if we are using steel coupling beams, and coupling beams are subjected to very large shear, we will get good ductility. But we have to take into account when we are using steel beams either embedded inside the RCC section or alone, then the anchorage into the shear wall, this portion is critical. So please look at this photograph here also. So this anchorage into the shear wall and anchorage into the boundary element of the shear wall, this is very important because the concrete below this steel beam has to transfer its stresses to concrete, and the concrete below and above this beam, which will be in contact, will be subjected to very high stresses, and that concrete needs to be confined properly. So another alternative of this type is given, where intentionally the portion of the beam inside or within the shear walls is weakened, and this acts as a fuse, and the yielding will occur where we are having the minimum cross section, and which is here at the center. This portion will get damaged during earthquake, and it is replaceable. So it is connected to the rest of the structure through bolts, and it can be removed. So this practice is also being used where because if we are using RCC coupling beams, and those coupling beams get damaged during earthquake, and those will be the first to get damaged in case of a coupled shear wall. So its replacement or repair will be difficult. In such situations, this may be a good solution. Now this coupling, this length of the embedment in case of steel coupling beams, this length is important because when it will be subjected to bending or shear from this side, here we are going to have compression at the top, whereas here we are going to have compression at the bottom. And we can consider the stress strain diagram or equivalent stress block, and this can be analyzed to determine this length LE in such a way that the concrete here does not get crushed before yielding of this beam. So whatever is the capacity of this beam, the capacity of the concrete before crushing should be adequate. So some expressions are available in literature. I have given this reference also. So how much should be this embedment length? About that, expressions are available. We can use that. Now the detailing. So this will be anchored in the boundary element, and the concrete, as we have seen, that the concrete will be subjected to very high stresses, and the concrete may get crushed. So that concrete needs to be confined. So you can see how the confinement of the concrete is done. So an I-shaped coupling beam is used, and then this concrete here is going inside. Sometimes people are using plates in place of I-girder. I do not know how do they satisfy this condition, because the concrete below the plate will be subjected to very large stresses. So a flange section is preferable because that flange section is going to distribute the stresses in concrete over a larger area. If it was just a plate, the stress here will be highly concentrated. So I don't know how it will work. I have not found any literature also, but I am just raising a caution there that when you are using plate, be cautious, look into the literature. Design of that is going to be difficult. And not only that, the ends of this girder, there should be anchor bars. So 2 anchor bars perpendicular to the length are to be provided here. And these anchor bars can be either a hole can be made in the flanges, and then this can be welded to the web, or a half coupler can be welded at the top and bottom of the flange, and then these bars can be provided with the coupler. So details of this are also available in the same paper by Al Tawel, and that can be referred for designing of these steel. The last point which I want to discuss is that when we are having a small pier here, there is an opening in the wall by the end of the wall, and there is only a small pier here. So this pier will be subjected to very large forces. This is going to crack also, and this reinforcement here, this can slip because the force which is occurring in the shear wall will be transferred to this pier through this reinforcement. So this reinforcement should be adequate, and it should be adequately anchored. The corresponding detailing is available in ACI 318. So I just want to make you careful that wherever you are reaching such a situation where you are having a small pier by the end of a shear wall, the opening is located close to one end. This pier, a small pier, also needs to be detailed properly. So thank you. That's all I have thought for discussion today. We can take up the questions now. I will stop sharing my screen.
Okay, thank you, Professor, for excellent presentation. We'll take up questions one by one, and Arvind will also join me. Okay, so we'll start from the last question that we have received, and we will go upwards. The question is when to design shear wall as thin shell or thick shell?
See, thin shell or thick shell is coming in analysis. So we can model them as thin shell or thick shell. Design will be done as a section. So like we are designing a beam or a column, the same principle we will be using for all shear walls, irrespective of their thickness. But modeling, even using thin shell, is good enough, because thick shell is relevant when we are trying to determine the variation of the stresses across the section. So even if we are doing thin shell, it is good enough for our purpose.
Okay. The next question is about dual system. In dual systems, is it necessary that frame should be designed for 25% of total lateral load and shear wall need to take 75%? I think the code is very clear about this.
Yes, code is very clear. Why this question is coming again and again? Because people want to take advantage of dual system in response reduction factor. So response reduction factor for dual system is more, and that for shear wall it is less. So they want to take advantage of response reduction factor, larger response reduction factor. But my friend, nothing in this world is free. Everything comes with a cost. So you have to pay the cost.
That's right. What should be the starting scale of response spectrum, and what is the reference for the same?
Sorry, I couldn't get the first thing. Starting scale.
Starting scale, yeah, scale.
Starting scale. I couldn't get the question. What is meant by starting scale?
Yeah, it's not clear.
And what's the other second part? Reference.
What is the reference?
He is asking reference for the same. Yeah.
Reference means text for that. So response spectrum is available now in all textbooks, and A.K. Chopra's textbook is the best. So A.K. Chopra's book can be referred for that.
Right. So next question is how shear reinforcement is provided when shear exceeds the maximum limit, that is tau c max in shear wall.
So if shear stress is exceeding tau c max, you cannot depend upon the truss analogy. In what our code gives, the stress the shear design is based on truss analogy. In this truss analogy, the bottom and top chord are the longitudinal reinforcement, The vertical elements are the transverse reinforcement and the diagonals are made of concrete. So when the concrete get crushed, when tau c or tau is greater than tau c max, then the concrete will get crushed. In that case, this analogy will not be valid. We have to depend on steel alone. And in that case, we have to provide diagonal reinforcement. Like in case of our coupling beams, when the shear stresses are greater than tau c max, we can't depend upon the concrete. We have to depend solely on steel in the form of diagonal beam.
Shall I
Arvind,
take
you can
further?
take it
Yeah.
next.
What
Yeah.
should be the diameter of rebars in web portions, specifically vertical bars, as code is silent? I couldn't understand. What is web portion? Is it
On
talking
the
about
diameter,
Yeah, that is
so
actually
I think diameter is related
middle.
with the thickness and maximum spacing. So diameter is related with thickness in IS 456 also. I do not remember, but there are limits on diameter in terms of thickness and spacing. So thickness will decide what maximum diameter you can go. Minimum diameter in any case is given in the code, and the maximum diameter will be decided by the spacing. If you will use larger diameter, then the spacing will not be satisfied.
Yeah.
So actually,
Next question is-
the question, one second. The question probably means actually for design of shear walls, excluding the portion that the boundary limit, the middle zone.
Acha, that is he is calling about
web.
web portion. Yeah, middle zone.
Yeah, middle zone of a shear wall where the clauses of column reinforcement are not applicable. So what should be the minimum dia? That is what is, I think probably he means.
I think normal wall reinforcement clause is applicable in that.
Right.
Yeah.
So IS 456 clauses
Yeah.
will be applicable there.
As there is an accurate intensity measure, say average, is there any average time period like T average considering all the modes?
No,
No.
there is nothing like T average, where you can take single value of assay and that will give you accurate intensity measure. I can understand this question, but it's not for this is somebody involved in research who is asking. So this is an advanced thing which we covered in some other talk, but not today. But yes, there is nothing like that T average. Perhaps it is not possible. What I understand that it is not possible to define a single value of T which will work in all time histories.
Yeah, and then you can.
Yeah, in case of irregular shape like L shape, can we adopt 2D analysis instead of 3D analysis to achieve economy?
I couldn't get L shape of what? L shape shear wall or L shape columns?
I think it means
Or L shape building.
Building, probably building, I think.
Oh, so building shape is L shape, and whether we can do 2D analysis or 3D analysis. I don't know anybody does in the industry nowadays 2D analysis, because doing 3D analysis is much easier. And it is only the life of the computer which is getting troubled. Life of the designer is becoming easier. So I think everybody is going for 3D analysis nowadays. Nobody, in fact, if you have to do 2D analysis, it will be problematic. You have to be very careful in making the model. So it is in no way economical. It is not related with economy. It is only related with simplification of the calculation. So earlier days when the computers were not available, perhaps that was an option. Nowadays everybody goes for 3D analysis, and that is much easier, and it is not uneconomical.
I think maybe he's not clear, but what I think what he wants to understand whether can we, is it necessary to consider the vertical component of the earthquake even if it is a irregular building. Actually, it is applicable for all the irregular building that you should analyze with considering the vertical component of the, maybe he's calling that as a 3D analysis.
Okay, so I mean, anyway, it is an interesting point. So as we discussed that vertical component in some cases may be critical, in some cases it may not be critical. But you have to identify in all cases that where it is critical, where it is not critical. So it is a good practice to do or to consider vertical component in all the cases. Wherever it is not critical, our design will not be affected or it will be least affected. If Earlier days, we have to do manual calculation and separate calculations for vertical components. Then, of course, it's a lot of trouble. But now, because we have to specify this only to the computer will take care of that. So there is
Right.
not much issue about it.
Arvind, yeah.
Yeah. In case of buildings, sometimes in RC column, maximum percentage is observed at terrace level. Can we provide lower percentage at lower levels and maximum percentage at terrace levels?
Yes,
As per-
theoretically, yes.
Yes.
Actually, at terrace level, the problem is that at terrace level, axial force reduces.
Yeah.
And the shape of the PMM interaction curve is such that with the reduction in axial force, the moment capacity reduces. So it can be provided, but it should be anchored into the lower story with sufficient anchorage depth.
And many times what happens at terrace level is when beams are of large span, actually total beam moments are transferred to columns. That's why many times the terrace level moments are
right. There is no continuous.
there is no continuity. Yeah, so that's why
that also increases.
So you can provide localized.
We can provide.
Yeah. Then for symmetrical building from stiffness and mass point of view, is it required to consider 30% from other horizontal seismic force?
See, when we are considering the other direction of the earthquake force, then it is having effect on beams and columns differently. Suppose there is an orthogonal building which has beams 90 degrees to each other. Then the y direction earthquake force will not cause any moment in x direction beams. But same is not true for the columns. Columns in any case, whether the building is symmetric, asymmetric, whether it is orthogonal or non-orthogonal, the columns are always subjected to biaxial moment. So that's why it is necessary, the code has recognized now, it is necessary in all the cases to take 130 combination. Especially in tall buildings where the biaxial behavior may be very significant.
Yeah, next.
Yeah, in bridges, we will check the ULS only for seismic, not the serviceability. Now, as per this code, you are suggesting to consider the bridges also of SLS in seismic, and there's a question mark.
No, in fact, it is other way around. Earlier, our current existing code is not asking to do any SLS design. Current, not the white circulation. White circulation, what will be there, we will see. But the current code, buildings, we don't do any SLS for earthquake. It is only ULS. But bridges, and in bridges also there are two different codes. One is by IRC, another is by railways. So railway code says that the bridge needs to be designed. The current railway code, the bridge needs to consider earthquake in SLS, and that governs the design. In most of the cases, actually, it is the earthquake SLS with earthquake which governs the design. But in IRC, they do not consider earthquake as part of SLS. They consider earthquake only as ULS. Now, what will be the approach in buildings now? Because they have defined an SLS, how they are going to use that SLS, that will come in this part too, when they will be talking about building design, that whether they are considering earthquake in cracking, crack control also, or they are considering earthquake only for interstory drift check, and how it will be used, that will decide. But in railway bridges, they are using earthquake to check even crack width, and that controls the design in most of the bridge piers.
Okay, there are a few more questions being added, Arvind.
Yeah.
So we will take
start
questions from the 5:30.
5:29.
Yeah.
5:29 we have to start.
Yeah.
That's whatever.
But that question, I think,
Yeah,
is
not technical
some criticism.
question.
Yeah, it's not a technical. It's a sort of a. So, is it necessary to design basement for passive pressure during earthquake, as they act as shear key for transferring base shear?
No, passive pressure. See, earth pressure acting on a structure depends on how much movement is occurring. So, for mobilizing active pressure as well as passive pressure, we need movement of the basement. So, when we are having a retaining wall, which is connected at top and bottom, then even active pressure is not mobilized. we have to consider earth pressure at rest. When the retaining wall is free at the top, the AC7 is very clear in this, the current AC722, it talks about this very clearly, that when the retaining wall is not connected at the top, it is like a cantilever wall, then it can move and it can mobilize active earth pressure. And we have to keep in mind active earth pressure is smaller than earth pressure at rest. So when our retaining wall is connected at top and bottom both, like it is part of the building frame, then we have to consider earth pressure at rest and then the dynamic component in it. Passive pressure is higher than earth pressure at rest, but it will require a lot of movement of the building towards soil, and that much movement does not occur. That's why passive earth pressure is not mobilized. At the most, active earth pressure can be mobilized, that too in those retaining walls which are cantilever. Otherwise, it will be earth pressure at rest in case of basement, because the movement of basement, even during earthquake, is limited.
Yes, Arvind.
Yeah. Do shear wall supporting beam should have thickness equal to 20 dia?
Yes, that's what we explained.
Yeah, 20 dia of reinforcement.
Right. If not, we should provide an element, a vertical element, similar to boundary element. We should provide a vertical element or a horizontal beam, which is satisfying this criteria. But that anchorage of 20 dia is necessary.
Next question is, sir, structural deflection shall be only checked in pure earthquake and wind case, or we have to check also in serviceable combinations like dead plus earthquake or dead plus earthquake? Why?
See, a normal symmetric structure will not be subjected to any lateral load under dead load and live load. Vertical load will not cause any lateral drift.
Yeah.
In case of a asymmetric structure, it is possible that the vertical load can also cause some lateral drift.
Some lateral load.
So now the code is clear that it is to be checked in combination. So it should be checked for the load combination. So because during earthquake, the dead load and live load will be acting, and due to that, there will be P delta effect also. So it should not only be checked for the combination, it should be checked for P delta combination also, P delta effect also.
Yes.
Where is the actual data to
That is again
support
April, yeah.
this? Okay, fine. Let's skip that.
Next is also a statement. You can take 534.
Yeah. While modeling transfer slabs in ETABS, the floor height to be considered is floor to floor or floor to transfer slab bottom or floor to middle of the transfer slab.
What is transfer slab?
Normal
I
slab.
think this normal slab or
Normal
the
slab.
diaphragm.
So the diaphragm, that means the slab which is monolithic with beam, integral with beam.
Yes.
Yeah.
So yes, it is a very interesting thing, and most of the people do it wrong, because slab has two actions in a building. One action is that it transfers the lateral load from one component to the other, and then it supports the gravity load, and it also acts as flange. Most of the times we ignore the flange action. The other two actions we consider, but the flange action is ignored, and that can be a problematic thing, because we have to satisfy strong column weak beam criteria. Generally, we satisfy that by taking beams as rectangle. And when we consider the flange, then that criteria may not be satisfied. Another misconception about flange beams or this integral slab action is that the flange is effective only in compression. No, the flange is effective in tension also, because the reinforcement which is acting in the effective flange width of the slab, that reinforcement will be effective in hogging also, and the hogging moment is going to increase because of that, and as a result the strong column weak beam criteria which we are satisfying may not be satisfied when we consider the flange action. So although it is difficult, I have seen in the field people do not take this into account, but I have an opinion that the flange section of the beam or effect of the slab in enhancing strength of the beam should be considered. And if it is giving us advantage in reducing the size of the beam, we should take it. It will increase our computational work. It will increase the job of a designer, but it may result in some economy, because if we take advantage of this flange action, the size of the beam will be less. And a smaller size beam, we will not require to provide larger column also. So it can be an economical solution, but of course, it needs more effort in modeling. And softwares currently are not that friendly to this type of model.
Yes, sir. The question is also about how to consider the floor height. Is it from floor to floor or the?
I mean, what is the
Floor to-
purpose of floor height? When we say floor height, for what purpose we are calculating that? Because beam will, any member we are modeling in our frame analysis, we are modeling
center
at the centroid of that member. So when we will be modeling beam, it has to be at the centroid of the beam. When we are modeling column, the model has to be at the centroid of the column. So it will automatically come. For what
Right.
purpose actually we are calculating this floor height, that's important. So I am not able to understand for what purpose this floor height is needed.
Correct. What value of modifiers has to be used for belt wall or outrigger
Sorry, for
when
which
they are
wall?
defined as? Pardon?
I could not understand that word. Which wall?
Belt wall. That is a
Belt wall. Okay, okay. So
Yeah,
in case of outrigger and belt system. Okay.
Yeah.
When they are defined as wall element.
Okay. So yes, what we can do is there are two sets of these factors are given. One for cracked section, another one for uncracked section. So we can perform first an analysis using uncracked section, see whether what type of stresses we are getting, and if it is cracked, then we can go for cracked section. I mean, this is what comes to my mind at the moment. I have not thought about it, but this is what we can do. Because if we are taking the outrigger and belt more rigid, our design will be non-conservative. So it should be on flexible side. The effect should be taken on flexible side. So wherever doubt, we should go for crack section. That will be more conservative.
Yes, Arvind.
Yeah. Next question is, shall we discontinue the boundary elements in shear walls in height when extreme
Yes, we
fiber
can
stresses are
discontinue.
less than 0.1?
Wherever the stress is below 0.15 FCK,
Yeah,
we can.
it's 0.15, but not 0.12. Yes,
It's 0.15.
It's
Yeah.
0.15 in our code. I modified it to 0.12 because 0.15 FC dash, slender strength. We are using FCK. So it should be 0.15 into 0.8. So that becomes 0.12 FC dash. So actually it should be 0.12. Our code has simply replaced FC dash by FCK, which is not correct.
Next is, while considering flange action, is it required to take 0.8 times length of the wall for shear stress calculation? Couldn't get this.
For shear stress calculation, I couldn't get that. Shear stress we will calculate over the whole section, and we will design only the webs to resist the full shear wall, full shear stress.
Couldn't get this actually.
No, maybe when the shear wall is provided with flanges, the total depth of that section generally is considered 0.8 times probably.
Yeah, that D is taken 0.8 times LW.
Yeah.
That is from a different region. That is because of the variation of the shear stress within the section. So shear stress is not uniform, and in our expression we are using it uniform. So that's why there is an equivalent. So that will be applicable in any case.
Okay. Yes, and next.
Yeah, response spectrum is constructed by SDOF. So how it is used for MDOF?
Okay, that's what I explained. That response or response of a multi-degree freedom system can be constructed using the response of a number of single degree freedom system corresponding to different modes. And there is a whole mathematics behind that, which I have not shown, but this is an accurate solution. There is no approximation involved. So there is a method of decomposition which utilizes the mathematical relationship of orthogonality between different modes, and using that relationship, the response mathematically, the response of a multi-degree freedom system can be related with the response of a series of single degree freedom systems. That's what we utilize, and response spectrum is giving us response of any single degree freedom system. So we get the response of all the single degree freedom systems and then combine that to get the response of the multi-degree freedom system. If somebody is interested in learning the mathematics behind this, then A.K. Chopra's book again explains this very nicely.
How much the seismic fragility curve from nonlinear static or the pushover analysis can be best used for seismic hazard assessment?
No. Both are uncorrelated. Seismic hazard assessment is different. Fragility curve is different. Seismic hazard is representing the demand. This is representing the natural phenomena. It has nothing to do with what buildings are existing there or not existing. Even if it is a free ground, there will be seismic hazard. The fragility function is the property of the building. That will depend upon how the building is constructed. Both are different. For calculating risk, we need both. We need demand as well as capacity. But demand cannot be calculated using capacity. So there is no relation between them.
What should be minimum thickness of shear wall that can be taken into consideration? So,
I have shown the requirements, IS 13920. Personally, I will feel that nowhere it should be used less than 200 millimeter.
Yeah.
Preferably 300 millimeter, but not less than 200 millimeter in any case. If it is a tall building, major tall building, then it will be always more than 300. But this issue will come only when we have a low rise or Maiwan type of construction. There also, I will insist on 200 at least.
yeah. Arvind, yeah.
Why short beams always showing fail in overstress in EQ design?
Okay, so there is a phenomena what we call short column phenomena, and same is applicable for beams also. So the shear demand in a beam depends on its moment capacity and span. So there is an equilibrium relationship that V is equal to M1 plus M2 by L. So if we go on reducing L for same M1 and M2, the V will go on increasing. So the shorter beams, for example, when we are having beams over the corridors, it will be impossible to design those beams for shear. It will be always overstressed. And what people do to satisfy it, they increase the depth. And when they increase the depth, the moment capacity again increases and the shear demand again increases. So if you are caught up in such situation, then try reducing the depth of the beam. Then perhaps it can survive. And if you are not able to design in any case, discontinue the beam there. Just continue with the slab. So slab, rather than being designed as two-way slab, it will act as one-way slab. And the beams we can avoid over corridors.
Sir, but what happens in practice is many times these beams between two walls or shear walls has got a vertical load also by some cross beams or something like that. So you will not be able to remove them. Then you get in fix.
So I will suggest that we provide a wider beam of lesser thickness.
Yeah, wider beam we can provide.
Or increase the thickness of the slab in that location.
So almost similar situation we face during design of coupling beams.
Yeah,
so,
coupling beam also there is very heavy loads many times comes because of the planning. And then it is vertical shear is also predominant. Okay.
I mean, that we should take care at the planning stage. Supporting very heavy load on coupling beam is very dangerous. Because coupling beam is going to fail first during earthquake.
Because the code actually has a particular requirement that any coupling beam should not have any secondary beam resting.
Yeah, it should have. It should not have actually.
I mean, if it comes in the code, then it becomes. But we have to use our engineering knowledge and judgment also. I mean, if somebody is putting a heavy load on the coupling beam,
There is not.
Yeah.
Not a sane decision.
Yeah. Next question is,
Yes. Yeah, please.
can we remove the cross ties links up from all the vertical bars in mid zone of shear wall?
Okay, so whether the cross tie should be provided in the middle portion or not? Is that the question?
Yes. Yes, that is a question. Yes.
It should be provided. It should be provided there also. Our code doesn't talk about that, but ACI 318 gives the detailing for that.
Next is for detailing of H piers in cutout. Is cutout even possible even though fouling the same detailing? Some language issue is there. But I think the meaning is where H piers cutout is possible or not. Should avoid
H piers.
H piers.
H
Yeah.
pier.
Yeah.
What is H pier?
Maybe a shear wall with opening
Yeah.
he is talking about, and H pier with the two sides of the openings.
Okay. So what is the question there? I mean, in such case,
That's not clear because already there is a cutout. That's why there is a H pier.
right. So sometimes there will be H pier in shear wall, and that edge pier will be subjected to
maybe he is asking whether the cutout is possible in boundary element.
Okay, so whether the cutout is possible in boundary element.
Yeah.
So this question is something similar to whether a cutout is possible in a column. So we can't. In that case, we should modify our shear wall. We should put boundary element on the other side of the opening.
Yeah, next time.
Okay, in shear wall where we having a door opening, generally we face a shear failure at that junction. For this, what can be your suggestion for a designer? So I think again the question is about shear wall with an opening.
Right. So shear wall with opening, the opening cannot be up to boundary. At least the boundary element has to continue. So opening, when we talk about the shear walls with openings, we talk about smaller openings near the center. That's what the code talks about, shear walls with opening. We can't puncture shear walls at number of places and still treat it as a shear wall. So very close to the boundary elements, it can't.
Yeah.
It should be near to the center.
Okay. The next question is, in equivalent frame method, how a C-shaped shear wall is designed or analyzed as a single section while it is modeled as 3 equivalent columns?
I couldn't get the question. So perhaps it is related with that model which I have shown, EFM, where I have shown a C-shaped wall, and in that C-shaped wall, 3 columns were used, 1 for web and 2 for flanges. And each column will get its own axial force, shear force, and bending moment. So the question perhaps the person is asking is how that shear wall will be designed, because we are getting 3. So in this case, what we have to do, whatever 3 columns we are getting, we have to integrate those forces on single section from 3 beams, 3 columns, and then those the section as a whole will be designed.
Okay. The next question is, in ETAS, while performing response spectrum analysis, the designer has to apply initial scale factor. What value that we have to consider?
Sorry, which factor? That I could not get.
Initial scale factor.
Okay, I think this is the question which was before we started, perhaps. I also read that. Okay, so is it related with period time effect or what?
No. That must be related to the scale factor for the base shear.
Scale factor.
Yeah.
Okay. Yeah. So when we are giving response spectrum in the software, we have to give a scale factor.
Yeah.
So what should be that scale factor? Okay. So if you are giving response spectrums, it will depend upon what response spectrum you are giving. So if you are giving response spectrum as the shape starting from 1, then the scale factor will be Z by 2 into I by R into G, because SA by G is coming from this. If you have already multiplied your response spectrum by Z, then scale factor Z will not be there, and so on. So total should be Z by 2 into I by R into SA by G into G, because this should also be made clear that whether the software is accepting response spectrum in terms of G or in terms of meter per second square. So if it is accepting in meter per second square, then do not forget to multiply this by G. So that should be our initial factor. And the second factor, of course, will be obtained by doing BB bar by BB correction.
Yes, Arvind.
Next question is actually earlier question is corrected. What should be the starting scale is to be used for the response spectrum in analysis in ETABS during analysis, initial
Yeah, so
analysis.
as
That
I
is
said,
the same
that's
thing, I think. Yeah,
same
just
thing.
now you mentioned.
So,
Yeah. Just now you answered the same question.
yeah.
Next is according to IS 16700, drift limitation for wind is mentioned as unfactored loads, while for interstory drift for EQ, it is mentioned as factor load combination. So how can we exactly extract the values? Should we consider the combinations, or should I consider EQX or EQY for drift value? What is that?
No, I couldn't get wind and earthquake. We never combine. So
Yeah.
separate analysis will be done for wind.
Yeah.
Separate analysis will be done for earthquake. We
Earthquake.
will take different stiffness in case of wind. We will take different stiffness in case of earthquake. And whichever is giving us higher forces, that we will use in our design.
And next is deflection, drifts, torsion for tall buildings shall be checked in SLS. Is a question mark. Yes.
The drift check which is given in our code, IS 1893, that is not SLS. In case of earthquake, the displacement is not an issue of SLS. It is not issue of serviceability. It is issue of limit of collapse. So when we are saying interstory drift of 0.4%, actually it means 0.4 into 5, 2%, because we are doing analysis for reduced earthquake force. So actually we mean 2%. So this 2% is against collapse. At 2% interstory drift, we are not expecting our structure to remain serviceable. We only want to ensure that it should not collapse.
Yeah, and then next.
Okay, since we design buildings with 1.5 factor of safety, should we divide the drifts obtained by the same factor of 1.5 for serviceability check?
No, it's actually same question.
The same question. So
Yeah.
as I explained, that is 1.5 is not a load factor. First of all, we have to understand this, that 1.5 factor we are not using, we are using is not a load factor. It is actually a correction factor. And in few months, this will be done away with that. When this wide circulation code is accepted, this confusion will not be there.
Okay, let us.
I'll take 542. Sir, some models are modeled by connecting beams to column centers while they are connected to the edges of the column at site. How far is this practice correct?
So beam at offset with column.
Yeah.
That's the question.
Yes.
So beams can be done with offset, but with column. But we have to ensure that the beam reinforcement, first of all, this offset should be taken into account. The difference between the center line of the beam and column, that should be modeled through offset command, because it will cause additional moment. And then the detailing of the beam column joint, that has to be done as per IS 13920, because the overlapping portion in beam and column only has to be checked for shear stress.
The next question is, how can the span to depth ratio of 1/4 for beam made applicable, because the beam will be too weak and will not form a coupling beam? For a coupling beam, span to depth ratio of 1/4 cannot be followed. Kindly suggest.
The question is not exactly clear to me.
Yeah.
So he's talking about coupling beam.
There is a definition of coupling beam in I 13920 that the span to depth ratio should be 1/4, L/4. Clause 6.1.3. Shall I? 1 second.
So if that is available, could you open or I can?
I'll just try to read out that.
Hmm.
13920. I'll take 2 minutes. 6.1.3, no?
Yeah.
Yeah. Yeah. 6.1.3. Yeah, beams shall not have depth D more than 1/4 of clear span. This may not apply to the floor beam of frame staging of elevated RC water tanks. But this is a definition, general definition actually. Not,
Right.
Yeah, so whether this general definition is applicable for coupling beam? That
No, not for coupling beams.
Yeah. Okay.
This is for the beams
Yeah.
whose design will be governed by flexion.
That's,
So normal beams should be governed by flexion, not by shear.
Yeah.
So for those, this definition is there.
Okay. Shall I add steel plates in shear walls when tau c exceeds the limit? Maybe he's talking about a composite.
Composite coupling beam, T plates.
Yeah. Yeah.
Steel plates or T plates? What he has
Steel plates.
Yeah. Yes, that's what we were discussing. We can include steel plates, but the problem is how to satisfy the embedment length criteria, because embedment length criteria depends upon the stress in concrete. And if we are embedding steel plates, then I'm not sure whether that criteria can be satisfied. So that needs to be checked. On the other hand, if we are using a beam section, I-beam, then it can be done.
Yeah, Arvind, next question.
Yeah. Next is, as per IS code, is it possible to provide a columns 1000 by 1000 at lower floors and then it's converted into a shear wall 300 by 2000? This is required in few cases at basement levels. How can you do it? No, you can't do
Column
that.
cannot be converted into shear wall.
Yeah. It's not. But anyway, it cannot be more than 1000, no? Because maybe 300.
I mean, if some cases, suppose somebody wants to do it really, I mean, where the bottom portions we are having columns, and the top portion we want to have a shear wall.
So maybe 1000 by 1000 column and then 300 by 1000 shear wall on top. Is it possible?
The
That
shear
may
wall
be the
can be
case.
even larger than the column dimension. If that is the case, then you have to provide a transfer story. So a deep beam of almost full story depth is to be provided below that shear wall.
But if it is within that column dimension, then whether the upper floor can be designed as
If
shear
it is
wall?
within that column dimension, then it is okay. Then I don't see any problem. So if we are having, let us say 1000 by 1000 column, and then we convert it to 300, but 300 by 1000, will it be a shear wall? I don't think.
Yeah, but in any case, we should avoid sudden change of thickness.
Sudden change is not possible until unless you are having proper transfer mechanism. So you have to carefully design a transfer mechanism whenever you are doing change. Otherwise, every lateral load adjusting column should have a continuous path from foundation to roof.
Yes, Arvind.
Next is generally in buildings having close to 14 to 15 story building, we find the drop in storage shear between 8 to 9 floors, then again it rises. What could be the reason behind this behavior?
Storage shear cannot drop.
Cannot drop.
Because whatever force is coming from the top story, it can be only added. It cannot go in the other direction.
Maybe he is talking about individual based shear, not individual component. Not
floor load.
Cumulative.
Floor load may be there. There may be a drop in the floor load.
Floor load.
There cannot be drop in the story shear.
Yeah.
Okay, the next question, is it necessary to scale? Okay, is it necessary to scale response spectrum base shear in service model?
Is it necessary to take?
Necessary to scale response spectrum base shear in service model.
Service model. What is meant by service model? Because in case of earthquake, do not have any service model. It is ultimate limit state model only. So not clear. Perhaps they mean that, okay, I got it. So for the purpose of satisfying the interstory drift, whether we have to consider scaled base shear or unscaled base shear. This is a question. This is a major issue. So when we are calculating the displacement, we have discussed that the shape of the response spectrum, acceleration response spectrum and displacement response spectrum is very different. With period, acceleration reduces, but the displacement always increases. So when you are considering a longer period in your model, the displacement is already on conservative side, whereas the forces are not on conservative side. So the purpose of scaling of the base shear is to take into account the effect of a possibility that the period may be lower than what we are calculating. So that uncertainty is taken into account. So scaling is needed only to scale forces. There is no need to scale the base shear while checking the interstory drift or deflection. So their scaling of the base shear is not needed because we are already estimating the displacement on conservative side. IS.
Okay, the next question is that 65% of mass participation should be in first three modes only, or it should be summation of first three governing modes in each direction.
Again, that is also a confusion. Code is not very clear. What do they mean by that? So my understanding is that what the code tries to say is that the modes may be coupled. So you may not get a unique mode or modal participation of the first mode in X direction only. If it is coupled mode, the first three mode may give contribution in X, Y also. So if we calculate the total contribution in the first three mode in X and Y, both should be more than 65%. So if I am getting, let us say, the first mode in X direction alone, second mode in Y direction, and third mode may be rotation. So in that case, the first mode contribution itself should be 65%. Not 1 to first, fourth, and sixth will be 65%.
Okay.
So first,
if there are clear-cut governing modes, then also this is applicable.
The clear-cut governing mode only I am saying, because why this code, I do not know what is the understanding behind this clause. So this is to define regular buildings. So it is in the form of irregularity it is defined. Why it is needed, I do not know. So, but regularity may be in, if a building is regular, then one of the property of a regular building is that it will have significantly large contribution in the fundamental.
Yeah.
So the first mode itself should have 65%. And then we should consider 90% total mass participation, out of which first mode itself is having 65%. Now, why they are talking about three modes then? So three modes is perhaps because the modes may be coupled, and single mode may give contribution in X direction as well as in Y direction.
Okay.
So can we add this mode 1, mode 2, and mode 3 X participations and Y participations and say that it is crossing 65%?
Right, I think so.
But not after. But not you cannot add one first, fifth, and seventh.
Right.
Even if it is governing mode. Even if it is governing mode.
Right.
Okay, Arvind, next year.
Yeah.
I think we are nearing 6:30, so we should take up another 4 questions.
Yeah.
We see that the questions are being still added.
Yeah. I'll just take important questions only now. So write in transfer consider for checking. So what stiffness modifiers for transfer beams supporting floating columns should be considered?
Stiffness modifiers for floating beams.
For transfer beams, that is
transfer beams, which are
transfer girders,
floating columns.
Floating columns.
I think because these transfer girders will also be subjected to yielding. I do not have a straight answer for this at the moment. But what I feel that whatever we are using for beam, same should be
Beams,
used
yeah,
for
we should-
transfer girder as well. Because it is expected that the transfer girder will also yield at the ends.
Right. Yeah, I think so. We should continue using the same stiffness modifiers as mentioned by the code.
I think these are. Can we provide brickwork in between two shear walls? Will it work as coupling or not?
Brickwork.
No, it will not work as a coupling, but it can.
Absorb some energy.
Brickwork cannot couple shear walls.
Yeah.
The coupling beam between shear walls is subjected to very high forces. So you can think of steel if you want to go beyond RCC, but you can't think of masonry or a weaker material for that.
Yes, I mean, we can take 553 maybe.
553. If the orientation of building is rectangular and the length is more in y direction, while doing gust calculation for crosswind, CF value, how do I calculate for x and y direction? Should we take direction as per orientation or wind applied perpendicular to the direction? So this is something.
So it's
Not
related
from
with
the-
wind. So what orientation of wind should be considered?
Yeah,
So I think
the
wind
building is
force-
yeah, building is rectangular.
so a rectangular
And-
building subjected to wind.
Yeah.
And which direction I should consider the wind?
No, the length is more in y direction.
Uh,
So while doing gust calculation for
gust
crosswind,
calculation.
gust calculation.
Oh, no, I do not know that. I have not studied wind that much. I can't answer.
Yeah.
Maybe somebody who has worked in wind.
No, but the question is not very clear at the moment. Okay, we should take up the.
Because gust will come into picture when the structure is very flexible. So if it is a rectangular building, I don't know what the question he is asking, and so I cannot even guess in which direction he was trying to ask.
Please suggest some guidance for usage of
Use floating
floating columns, when to use and when not to use in tall buildings.
Not to use.
Floating columns.
Yeah.
Floating columns can be used, but you have to design the transfer girder properly. So the transfer girder should be stronger than the columns. And second thing is that in case of floating columns, wherever we are having floating columns or transfer girders, construction sequence analysis is very, very important, because the forces in the transfer girder change drastically when we follow construction sequence analysis and we do not follow construction sequence analysis. So follow construction sequence analysis and design those transfer beams with some additional factor.
And plus, we have to use non-linear analysis or not.
Some analysis we have done, and one paper we are in the process of publishing also. Nonlinear analysis is not necessary.
Okay.
So, but shall we also check the displacement compatibility in this case?
Displacement compatibility between?
The floating columns and the other columns.
That will be automatically there when we are doing the analysis now. When we are making a computer model and performing analysis, the compatibility, the distribution of the stresses based on stiffness,
So for
that
the-
will be automatically.
For the R times displacement, because we want that to be in elastic stage throughout. The floating column should not be a part of the lateral load resisting system. That's what code
That we
says.
can't ensure. We can only ensure that our beam transfer girder, that should not yield. That should not form a hinge below the column. So if we ensure that, then it is okay.
Fine.
So there,
Because the
in
code-
case of a strong column weak beam, we have to do a strong beam weak column below the, because that will act as the foundation to the floating column.
So
So
because
this transfer girder is the key issue there.
code specifically mentions that the floating column should be out of the lateral load resisting system. That means it should be designed like a gravity column. That's what I was pointing out.
Actually, that will not help. That will rather, I mean, code has given that, you are right, but that will make this floating column even more vulnerable. So if you are designing it as gravity column, you will be designing the supporting girder for lesser moment, which will actually come during earthquake. So removing it from lateral load resisting system is not a good idea, because in reality, it will be resisting lateral load.
That's right. Okay, Arvind, next question.
Yeah. Next, as you mentioned, links are required in non-boundary zones in shear wall. Can it be eliminated for less than 1% reinforcement as mentioned in IS 456? Yes, I think.
Less than 1% reinforcement.
Yeah. In that means, can IS 456 be followed by further for the detailing? Well,
No, rather than IS 456, I will like to go to ACI 318.
okay.
Because IS 456 does not take into account the seismic behavior.
Oh, this is again basic question, but what will happen when we model column aspect ratio of less than 4 as a shear wall on structural behavior?
This is another important issue,
Yeah.
and we have had a one full talk on this.
That's why
What is the difference between a column and shear wall? So the difference between column and shear wall is not based on the aspect ratio. It is based on the bending moment. So you plot the bending moment along the height of that particular element. If it is crossing the zero, that means the direction of the bending moment is changing at top and bottom. It is a column. It will be detailed as a column. In that case, the plastic hinges can form at top and bottom of the column. It will be detailed as a column. If the bending moment diagram is like that of a cantilever, so it may be sawtooth type, but it is larger at the base and it goes on reducing along the height, then it is a shear wall. And then it will be detailed as shear wall, where the plastic hinge will form at the base and we will do ductile detailing at the base. So it is to be decided based on the bending moment diagram, not based on the size or aspect ratio.
So two last questions. One I will ask Arvind, you can ask the last question.
Yeah.
There is another one basic question. Is it flat slab system allowed in zone 3?
Sorry, is?
Flat slab system.
Flat slab
Allowed.
system.
Yeah,
Flat slab system is allowed in every zone, provided you satisfy the requirement of the code. So flat slab system is allowed, but not as a primary lateral load resisting system. Along with that flat slab, you should have sufficient shear walls, and that criteria is given in the code. You should satisfy that.
One next is how to analyze in vertical earthquake for heavy cantilever or span PT span beam 8 meter around in first to fifth podium level. Building is G plus 21. Whether you have to use response spectrum or time history analysis.
We can use both. We can use response spectrum as well as time history, but we have to keep in mind that it may be difficult to excite 90% mass in vertical direction. So to get modes, adequate number of modes, and if we are not getting that, we can in vertical direction we can use equivalent static method, and we can apply a constant acceleration in vertical direction, and the value of that constant acceleration can be calculated as given in the code in vertical direction, where SAYG value is taken as 2.5.
One more small but important question. 1893-2016 is silent for slab modifiers. That is true. What modifiers should be used for slab? They are not now given in 16700, so we can use them.
So wherever you need, you can follow ASC 41. ASC 41, whatever modifiers ASC 41 is suggesting, we can use that.
Yeah. I think we should close now.
We are coming to the end of this question and answer session.
Yeah.
Okay.
I think we can close.
So thank you for conducting this session.
Yeah.
Lot of questions were there.
Yeah.
Sir, I will offer vote of thanks
Yeah.
and few of the point. One thing is we will be circulating Google feedback form after, let us say, Wednesday. On 4th also will be of circulating vote feedback form. Please write down your question if it is not answered. That is one. Second question is, they will be getting PDF. That sir, you answer. If will you be sharing PDF format, then we can share with others.
Yeah.
PDF or slide. Hi, Yogendra sir, or he is there or no? That we'll check with Yogendra sir.
Yeah.
Recording, we may be in position to share after 1 week or so. And once again, thanks for attending in a very large number. We as Epicons consultant, we are into structural design, proof checking of tall building, structural audit, assessment and NDT, concrete quality monitoring, project management consultancy, architecture and detail engineering, and beyond that, of course, training through EFC. Few of the topics are already suggested in question. Thank you for listening, and we close here for today.
Thank you. Bye bye. Take care.
Bye.
Yeah.